So, for a beginning, we will start a little questions I have prepared for you. So, let's try to answer these questions. It will be a little preparation for a raffle on the evening this day. So, you can start a little bit to interact, to know everybody, how you feel. Has anybody problem with Slido onboarding? Well, starting, yep, 11 votes, perfect. Well, next one, let's see, what was your absolutely highlight from the day one? So I will close this one, start another one. What was your absolute highlight from day one? Let us know, because your opinion should have impact on the next KCD. So please be careful what you choose. Oh, workshops. I love workshops. Someone said that workshops, it is a work and shop. So first work and then shop. Well, deep technical debates. Wow, wow. Still workshops. And I don't know who was on the panel yesterday here, maybe a couple of you. And do you remember that there was a question for everybody about who is more dangerous, Junior with kubectl access, anonymous AI agent, a junior with AI agent whispered in their ear, and a senior who thinks they no longer need to check the agent's work. Yeah, absolutely. Perfect. Yeah, I will close this one, and I take my speech to you. So I'm stopping this. Thank you so much for answers. You see what others thinking. So, and I will restart this one. Well, and we are going online. Perfect. With the pictures. So. Good morning once again, Cloud Native community. Cheers for making it back for day 2. I hope everyone local's control plane nodes are reporting ready this morning. Or are some of us still stuck and crash loop back off after the social event last night? Personally, I tried a horizontally scale my sleep last night, but my internal scheduler declined to ignore my resource requests. So if I start hallucinating like a poorly tuned large language model, please just blame the Czech local beer. Yesterday was absolutely brilliant. We kicked off with Kasper Borg-Nissen, who reminded us that observability isn't just about the tools. It's about not being miserable when things break up at 3 a.m. We also had David Pech on stage, bringing actual solar panels and industrial funds. I am fairly sure that was the first time in the history of this university that Kubernetes talk actually caused a physical breath on the front row. And those lightning talks, 5 minutes of pure chaos. It turns out you can explain a complex monitoring stack in the time it takes to brew a proper cup of English breakfast tea. But that was yesterday. Today, our cluster is even bigger. We have packed schedule of deep dives today. If you want to suffer productively, there is a Kubernetes the very hard way. If you want GitOps in practice, there is Argo CD and Cargo. And later today, we go all the way to the edge with immutable fleet management, Bootsy, and flightctl. There is also a hands-on system design workshop for everyone who enjoys putting complex things together without pretending it's simple. If you are here for workshops like the Immutable Edge session, please make sure your laptops are actually charged. There is nothing less immutable than that battery in the middle of GitOps fleet management demo. And quick reminder, stay with us until very end. There will be a closing ceremony with legendary Raffle. We have got some fantastic prizes from our sponsors, including those world-famous Prusa 3D printers. So don't let your attendance be terminated before the final session. The coffee is hot, the Wi-Fi is almost stable, and the speakers are ready. So let's day 2 start it. And our first session begins in 5 minutes. Have a brilliant day, everyone. Thank you.
Okay, so good morning once again, everyone. In our first session today, Milan Toth will tell us why don't we actually need an LLM. So the stage is yours.
Thank you very much. So hello guys, my name is Milan, and I came here today to give a little bit of provocative session why we actually don't need LLM and what we can use instead during our day-to-day operations or not during day-to-day, but for actually four very kind of distinguished operations that we do with our platforms or with our clusters. So quick disclaimer, this is not an anti-AI talk, right? I like to talk engineering, and I'd like this to be a pro-engineering talk, right? So, and instead of focusing on tools, I'd like to talk about principles. So, yeah, we've seen it all. Many vendors shipping new dashboards and new features with a lot of AI buzzwords and whatnot. So I believe the mathematics underneath should be more or could be more powerful and more effective than using or throwing LLM into our Kubernetes operations. So we have 35 minutes, so let's go. As I said, these kind of things like anomaly detection, capacity planning, and root cause analysis, failure prediction can be solved with mathematical principles or formulas, and they have been defined by math for a very long time. I believe using a deterministic approach to deterministic problem is much more effective than using LLM, which is probabilistic, and it's cheaper, right? It's actually auditable, right? And it doesn't lock you into any vendor. So as I said at the beginning, four areas that I would like to focus this talk on. How big should the cluster be? Any metric, is it weird or it's just, you know, the Tuesday? What can break next and why it broke at 3 a.m., right, when we all rather sleep? Yeah, AI theater. Why AI theater? I believe everybody is kind of now with the AI on a gold rush, and I believe it's important to stick to principles and why we actually don't need GPU for everything. So first problem, how big the cluster should be and what we actually can apply to identify the right size, right, for the right sizing. First thing, queuing theory, which was first not invented but described by a Danish engineer, Mr. Erlang, in 1909, when he was trying to figure out how many phone lines Copenhagen needed, you know, so he invented the mathematics. And now we use it in telecoms, in call centers, we use it in hospitals. Even CPU schedulers use it. So, and Kubernetes pod handling requests is a queue as well. So we already know how to size queues exactly. Another mathematical formula called little law, where L equals lambda W, is the average number of items in a system, which equals the arrival rate times the average time spent there. So this is an identity. It holds in a steady state for any queuing discipline, and it's the one formula that I kind of become very fond of. There's a caveat to this. Little law is descriptive, not prescriptive. It tells you what L must be. It does not tell you how many replicas to run. L is concurrent in-flight requests, not replicas count. And W is the mean latency, not your P99. So it's actually a hook, but the actual sizing, a peak replica count where the weight probability drops below your target is the Erlang C formula. That's going to be on the next slide. And we still don't need GPU, we don't need training data, we don't need anybody. We can do this by ourselves. Yeah, couple 100 lines of Python sits between your metrics and your horizontal pod autoscaler. Here's what it looks like in practice. You scrape two things from Prometheus, request rate and mean service time, and both are already exported by every sensible service, right? So you already have those metrics. You feed them through the Erlang C formula on an MCQ, and outcome is a recommended replica count. One unit note, in case anyone is doing the math along with me, the scrape gives service times in seconds per request. The function takes mu as a rate. So we invert it internally. This is really rough formula, so it's not like you can copy and paste it, right? This is more kind of like a food for thought, and kind of like doing the exercise by ourselves somewhere when we have a free time. And this is supposed to serve as kind of inspiration. So this is actually the concrete example. This is the whole exporter, two functions. Erlang C gives you the weight probability for lambda, mu, and candidate replica count. A recommended underscore replica sweeps the replica counts until that probability drops below the target. So the return 256 at the end is a fallback. So if the system can't be sized with the cap, the gauge never goes to none. Wire this to Prometheus gauge, scrape lambda, and mean service time, invert the get mu. Now your horizontal pod autoscaler, your dashboard, your capacity meeting, all reading the same number, derived from the first principle, not vibes. This can be actually achieved in under 100 lines of Python code. This is, those are my empirical numbers from my experience. Not many of us have the luxury to actually play with the clusters or where we can add the nodes based on some kind of autoscalers, right? So often we play with the pods, right? Not with the nodes. We scale the pods, not with the nodes. I had the opportunity and luxury to work on some very big clusters in Europe, and those are my specific numbers. What I was able to achieve, not in terms of physical money saving, but if we would interpolate it into money, the ROI was this. This happened during the last couple of years. So the number is not really precise because the prices of the hardware kind of like fluctuates over the years of the time. So yeah, and really, I was running experiments on those clusters, and some savings were fictional because I wasn't really able to do the sizing of the cluster due to whether it was regulated environment, or there was no hardware spare to put into the cluster. Sorry. So another pillar of this talk about the metric that is going sideways somewhere. And for this, there was a method invented in 1924 called statistical process control by a gentleman called Walter Schubert at Bell Labs. He was trying to figure out when a manufacturing process was actually broken versus just noisy, right? So he invented control charts. Toyota uses them now, pharmaceutical industry use it now, and semiconductors use it, so we can use them for the pod CPU as well. What's the principle? The control charts are simple. You compute the mean and standard deviation over stable window. Anything outside these three sigmas is an anomaly. The math gives you the false positive rate in closed form, about 0.27%. One honest caveat, the exact number assumes Gaussian data. CPU isn't quite Gaussian. It's bounded, sometimes skewed, sometimes bimodal, so the real data drifts a bit. But for production system, also layer multi-sampler rules and cooldowns to keep alert volumes sane. But the point holds. You pick the false positive rates, you can defend it. Try to get this with LLM. False positive rates are bound and known. You pick the rate, you don't pray, right? This is the headline benefit. False positive rates are bounded and known. 3 sigmas gives you 0.27%. 2 sigmas gives you 4.55%. So if you compare this to AI anomaly detector, which doesn't use math, even if the AI anomaly detector would use the math, it's actually anti-pattern to use LLM for mathematical and deterministic problems. So this is the whole alert from QL, right? You take the CPU utilization, you compute a rolling mean and standard deviation over an hour, alert when the current value drifts outside 3 sigmas. That's it. Again, this is not exact science, what I'm presenting now, right? Rather, I would like to add some honest notes. First instance, the node CPU utilization ratio is recording rule you define from node CPU second total. The existing stack doesn't ship a CPU usage gauge. You have to derive it. And the second, the offset 5 minutes on both recording rules is deliberate. It excludes the most recent samples from the baseline. So otherwise, a sharp anomaly pollutes the very mean and standard deviation it's being tested against. Again, you don't need any training data. You don't need any model. You don't need to call any API. So from day one, you can use this. Again, those are my numbers from my empirical my empirical samples. This is the the statistical process control conservatively recovers 8 to, or at least to me, it helped me 8 to 15 hours a month that I burned, on false positive pages. On a 10-person platform team, you can do the math. That's quite some time, so during a year. So another pillar that I would like to discuss is root cause analysis, the category where AI feels the most magical, right, and is actually the most dangerous. Many of you have been administering system where the spam detection was running, right? And we know this Bayesian networks since 1988, right? Mr. Pearl, he won a Turing Award for this. So what is Bayesian network? I will cite the literature. It's a directed acyclic graph. Each node is a variable, and each node carries a conditional probability given its parents. So when an incident fires, you run inference over the graph. Outcome is a ranked list of likely causes with probabilities attached, right? Again, you need a formula for this, or you need an algorithm to do this, but I believe if I was able to do it, anybody is able to implement Bayesian algorithm on their own. So here's the critical part. For any of us who had to do a post-incident review, every answer is auditable, right? You can trace exactly which edges fired, which priors moved, why one cost ranked above another. So I have used LLM to do a postmortem, these GPT models to do some root cause analysis. But sometimes the data are very sensitive. You don't have the luxury to use the LLM, or even the connection to the internet might not be available. So, so only auditable and audited tools can be executed on the cluster itself. So yeah, this all comes together, into the stack, and how does it plug into a real stack? We all love OpenTelemetry, right? And OpenTelemetry traces gives you the service graph for free. So 2 honest notes before you walk away. This is a plug and play. First, real service graphs have cycles, right? Shared services, callbacks, event-driven flows. Bayesian networks needs DAG, so you break the cycle first, you drop the weak edges, use the dynamic Bayesian network with the time index nodes. That's why the slides becomes the DAG, not is. Second, learning conditional probabilities from incident assumes you have labeled incidents. Many teams don't. So hand authoring works for small graphs. For large topologies, you want a hybrid. New incidents comes in, you run inference, and you get wrong ranked causes. The graph is the explanation. Measurable. Mean time to recover. Teams that ships Bayesian root cause analysis on top of their open telemetry data typically cut mean time to resolution noticeably. The exact number depends on your incident base rate. So, but more importantly, every output is explainable, right? So you really are able to explain what have happened. And every output is auditable. Again, I came from work in regulated environments where you don't have the luxury to plug your MacBook into any tool you wish. So the fourth, the last pillar of this talk is what will break next, right? So what can actually break? So let's play this game of trying to find out what can happen. So this is the one the vendors are the most excited about right now, because AI can really predict, incidents, and AI can really do anomaly forecasting. And it has been solved deterministically, so in case you wish, you can look at it from another point of view. It's an entire field for this, and it's called survival analysis. So Mr. Weibull in 1951, Kaplar and Mayer in 58, this is the math. Insurance actuaries use to price your life insurance. The aircraft maintenance crew used to decide which parts to replace next, and the cancer trials used to compare treatments. And critically is the math hard drive manufacturers have been using since the 90s to fit the smart data and predict disk failures. So we are not inventing anything, we are catching up. Throwing LLM to all these problems, you might be losing details, and you might give up some auditability. So here is the entire toolkit on one slide. It's the reliability function. It's probability that a component is still alive at time t. Right? So 2 parameters to fit. ETA is the characteristic life, the time scale of the system, and beta is the wear pattern. Less than 1 means infant mortality, equal to 1 means memoryless random failure. Greater than 1 means wear out. So then you plug in T, how long the thing has been running, and 2 parameters, closed form, fit from your own incident history. That's your predictive maintenance system. Again, the math has been here for a long time, been using in a very, very critical parts of our lives, and businesses that are fueling the economy, and it can be also applied to Kubernetes operations reliably. So how it actually plugs in, Your cluster is already emitting everything you need. Certificate expiry, Cert Manager already publishes no after, predicts the storm before the page arrives to your phone. Again, some side notes on certificates. Strictly speaking, certification expiry isn't a survival problem, right? It's a timer math. Not after is known exactly, but it feeds the same maintenance scheduler that consumes the Weibull and Cox outputs. So I'm bundling it here. Disks and PVCs, smart metrics, fit and variable replace the volume before it dies. So this applies to nodes, memory pressure trajectories. You can replace the node before it OMs. Again, you don't need model, you don't need GPU, you don't need API to call. A little comparison of the math versus LLM for these 4 problems, side by side. Mathematical or math is cheap, it's auditable. It has bounded error, right? So we can really say how precise we are, and it runs on what you already have. LLMs are expensive per query, they have unbound error, right? They hallucinate and they need GPU and a lot of inference. So for these 4 problems, and I'm only talking about these 4, the math wins over the axis. That matters, at least for me and my operations and what I do. I don't have the luxury to use LLM all the time, at least not outside my home. But for the work, I don't have the luxury to use the LLM. Again, this is not the anti-AI talk. Here is what I believe LLMs do earn their keep, like natural language interface to your cluster, right? Summarizing 1,000-line stack trace, drafting runbooks, reading and writing YAML files, and anywhere the input is a language and the output is language, LLM is great. Just don't ask them to do the arithmetic. Cloud-native computing foundation stack ships the instrumentation. It leaves the math to vendors, right? So we have all we need. We have all the tooling. We just need to plug in a little bit of creativity inside to achieve the most precise results, because it's kind of not my hobby, but I believe the right-sizing Kubernetes is a business problem, and right-sizing Kubernetes determines whether your operation is economical or not. So Prometheus gives us metrics, Kida gives us auto-scaling triggers, Kubeflow gives us ML pipelines, and OpenTelemetry gives us traces. What none of them ships is capacity planning, statistically anomaly detection, failure prediction, or probabilistic root cause analysis. Yeah, you can use, for example, the horizontal pod autoscaler in recommendation modes and stuff like that, but the gap is there, and you can feel it. Approximately 200 lines of math. You don't need any AI. 4 tools, they all read what you have. All write back what you already consume, right? The integration story is honestly boring, which is the point, right? Queuing theory exporter reads Prometheus, writes Prometheus, your HPA consumes it. Statistical process control alerts. Pure PromQL recording rules lives in your existing alert manager. Variable fit reads certification manager, smart metrics, not telemetry, writes a Prometheus gauge for your maintenance scheduler that reads it. And the Bayesian root cause analysis solution consumes the OpenTelemetry traces, expose an API. Your incident bot already knows how to call. 4 tools, no new infrastructure, no new vendor. The decision framework, how to decide, this is the part you can actually take home in 3 steps, and you can use it next time somebody pitches you an amazing tool. Classify the problem. Deterministic with closed form answer. Statistical with known distribution. Casual with known graph. This is what I did. I spent a week with the math. First, read a couple books, couple papers, talked to my friends that are actually mathematicians, because I'm not a mathematician, I'm not a scientist. Reach for machine learning only when the input space is genuinely unstructured. Logs you've never seen, free text incident reports. I have some toolkit available, but I'm not publishing it. If somebody is interested, I can, upon request, share. Caveats, because I'm an engineer. Queuing theory assumes poison arrivals, usually true. Check yours. Statistical process control assumes a roughly stationary process. We have 5 minutes left, so I will speed up. Again, these are my numbers. Doesn't have to be yours. Just sharing what I've learned and what I've experienced. Those are the 4 names to remember. And I would like to end the presentation with one funny quote. I like to, beside computer engineering, work in a workshop, right? And between my friends, we have a note or a joke that the one who dies with the most tools wins, right? And I kind of find it funny to apply to the optimized cluster. So you can print it and stick it somewhere if you want. Thank you very much. Any questions?
Yeah, the first one is just thanks for right now.
I think they don't know. They simply don't know the tool they can use, because we are being bombarded with tools, right? It's tools epidemic and tools for everything, especially in the cloud native space. We have many, many tools. And it's kind of, to me at least, right? Not some Altman. I don't know. I don't know much about GPT because I'm not an AI expert. Would be correct to say that Bayesian network with self-attention is GPT type of large language models? I don't know. I don't know anything. I don't know everything, right? So, is Bayesian RC root cause analysis prone to survivorship bias? Maybe yes, maybe no. I don't know. You were talking about some Sigma tools. Do you think 6 Sigma Bell certifications are valuable for DevOps? Honestly, depends what you're looking for in your life. I don't have any certifications, right? The only certification I have is the driving license for a tractor, so, and to operate a chainsaw, because my former study subject was a forestry. So but that was a very long time ago. And at the faculty of the forestry in the Zvolen University, I become very fond of science and math and statistics, and this is what I took from my university years to my IT profession. What would you use to measure the average request throughput of a service? How do you handle peak time and little to no traffic overnight, etc.? How would you handle peak time and little to no traffic overnight? I don't really understand what you mean by how do you handle peak time and little to no traffic overnight. But how would you measure the average request throughput of a service? I put a little formula how you can actually measure the average request throughput of a service. So you can take the response time of endpoint, for example, and create a very simple mean average. Which observability tools do you recommend to use? Well, for Kubernetes, the choice is obvious, at least in my opinion. I like to use Prometheus. I like to use Grafana. I used a lot before in the traditional server landscapes. I use a lot of Elk Stack, Elastic, Logstash, and Kibana. And I do a lot of custom tooling development for my customers or for my jobs. But I use the OpenTelemetry as my main stack. Thank you very much.
Okay, so the next talk will be by Scholz, and he will talk about the reality versus expectations of in-place CPU and memory resizing. So the stage is yours.
Thanks, and welcome everyone to my talk. My name is Jakub. I work as an engineer at Cloudera, and I'm also a CNCF ambassador, and I am a co-founder and one of the maintainers of the Strumzy project. And Strumzy is all about running Apache Kafka on Kubernetes, and Kafka is one of the bigger workloads. Well, these days nothing is bigger than AI, but Kafka is still quite big, and it's quite hard to size the Kafka clusters. So that's why in Strumzy we are always looking for things such as auto-scaling and things like that to kind of make the Kafka clusters a bit more efficient. And 2 years or a year and a half ago, I did a talk about horizontal auto-scaling in Salt Lake City at KubeCon, but Kafka scales very nicely horizontally, but it isn't very elastic because it has all the stateful data. So when you are scaling it horizontally, you have to move the data and so on. So it's not something you can use to kind of scale up and down every 5 minutes. So that's why the vertical auto-scaling has some appeal for us as well. And that's why the in-place pod resizing feature seems really interesting, or seemed really interesting. And that's why I started looking into it. And in this talk, I will first kind of give you some introduction of how it works. And then in the second half of the talk, I will talk a bit more about the practical experiences, the various gotchas, limitations, and things to be aware of. So just to get started, the in-place pod resizing was introduced in Kubernetes 1.27. But what's probably most important, it moved to stable and GA in 1.35, so it's now enabled by default. You need it supported by your container engine as well, but I think it's supported in all the recent versions of Cryo and Containerd and so on, so that should not be a problem. And what it does, it allows you to change the memory and CPU resources allocated to your pods and to your containers without restarting them. And that's great because less restarts means less disruption. It makes vertical auto-scaling much easier. And it also allows you to kind of think about some special use cases, such as having some startup CPU spikes handling, where you have a bit more CPU at the start, and then you lower it down, for example. So how does it work? When I talk about it with various people, a few times I notice that they somehow think that with the in-place pod resizing, they just edit the deployment or the stateful set or whatever they use, and it will kind of magically resize the containers without the restarts. Well, that's not really how it works. If you just edit the deployment or the stateful set and change the resources there, you will get the same rollout as you have been getting in the past, so nothing changed there. Instead, if you want to use the in-place pod resizing, you have to edit the pod, and you have to use this special resize sub-resource to kind of resize the pod dynamically. And of course, resizing the pod doesn't have any impact on the other pods managed by the same deployment. It doesn't in any way change the deployment or the stateful set. So if you want to do that as well, you would need to do that separately. So let's have a quick look at a short demo. So I have here my deployment already running. It has a single pod. It's just a simple. So let's first try to do kubectl edit deployment. And let's edit the deployment. So it's just a normal deployment. And let's find the resources. And let's change the resources to 600 milli-CPUs from 500 milli-CPUs. Let's apply the changes, and as you can see here on the side, exactly what you would have normally expected happens. The new pod is rolled out with the new resources, and the old pod is deleted. So instead, as I said, we have to actually edit the pod. And first, let's check the status section, because in the pod status section, you have actually the container statuses section, and that shows the resources configured for this container. And you can see that's the 600 milli CPUs we just used in the deployment and 2 gigs of memory. And then, of course, in the spec section, there is the desired resources configuration. So let's give it a try and change it to 800 milli CPUs. And now let's apply the changes. But here at the bottom, if you check, I'm now not just doing something like kubectl apply or something, but I'm invoking the resize sub-resource, which will make sure that I just resize this pod. So I run it, and if you noticed on the side, kind of the pod blinked few times as it was updated. So let's close the editor and let's just get the pod YAML. If I manage to stop making typos. And if we check the status section, now here we can see it has the 800 milli CPUs, which I just configured there. So the status suggests that we have resized the pod successfully without any restarts. But just to make sure, let's do kubectl exec into the pod. And let's check this C group information about the CPU we are using there. And you get these 2 strange numbers, and you actually have to divide them to get the actual CPU you have. So in our case, it's 80,000 and 100,000. So if we divide that, we get 0.8, which is exactly the 800 milli CPUs which we configured the container with. So you can see that kind of the resizing didn't just show it in the pod status, but it actually also showed in the actual container in the C groups, which you can see there. So now, the interesting question to talk about as well is what happens when there's not enough resources, because I really just bumped the CPU resources by a little bit, just by 200 milli CPUs. That's not much. But there are these kind of special states which might happen if you do some bigger changes. One of them is, it's called infeasible resizing. And that's basically if you would try to resize the pod and the containers inside to the amount of resources which are not available in the node. So in that case, it would kind of move to this infeasible state where kind of Kubernetes knows that, yeah, this will never resize because the node simply doesn't have the capacity. And then there's other state, which is, let's say, slightly better, which is deferred resizing, which means that in theory, one day, this resizing might be possible because the desired size, it's not bigger than the capacity of the worker node. But right now, this resizing, it's not possible, maybe because other applications are running there and they are kind of taking the space. And that's why the resizing is deferred. And maybe one day, once the pod move away, the resizing would actually happen, because then suddenly there would be free capacity for that. So let's have a look at another quick demo. So let's exit from the pod where we were running, and let's edit the pod again. And this time, let's try to increase the CPU properly, and let's go from 800 milli CPUs to 800 CPUs, just a little bump. So I will use again the resize sub-resource. You can see on the side it's still updated the pod, but when I actually get the YAML of the pod, you will see the resizing didn't happen. The container status still says it has only 800 milli CPUs. And when I scroll up and go to the conditions, I will see here that, yeah, the pod resizing is pending. And the reason for that is that the resizing is infeasible. And it's basically because, yeah, I requested 800 CPUs and my node has 10 CPUs. So, well, that will never happen, right? So let's try to do the other case. as well. And to make the math easy, let's go for the 10 CPUs, which is the node capacity. Let's resize it again. And let's check what happened here. And still 800 milli-CPUs, still nothing happened. When I go to the conditions, now it actually changed. It's still pod resize pending, but this time it's deferred. The reason for that is that I requested 10 CPUs. 10 CPUs is actually the capacity, so in theory it might fit, but there's actually 750 milli-CPUs in use, and so it cannot be resized right now. Now, just in this simple demo, the reality is that the 750 milli-CPUs, they are used by the networking, monitoring, and so on, so they will probably never go away. But if these were some other applications, then maybe they would restart, reschedule to a different node, and the resizing would actually happen. So another thing to consider is that so far I have been changing only the CPU, right? And there's a reason for that. CPU is a compressible resource. I'm not sure if everyone knows what compressible resource means, but it basically means that the applications handle it pretty well when you change the amount of CPU they have. So if you have some process which is running with some CPU capacity, then that kind of defines how many CPU cycles does it get, how much time on the CPU, and if you give it a little bit more, then yeah, it just gets more time, it finishes the job faster. If you give it a little bit less, then it will be a bit slower, it will get less time, it will take more time to complete, but in general it works, at least unless you make it really, really, really low, that you cause some CPU starvation. But with memory, it's a bit more complicated, right? Because if you have an application which is using 2 gigs of memory to store some data in the memory, you can't just come and say, okay, I'm now taking away 1 gig of memory. You wouldn't really expect such application to survive when you just remove half of the memory it's using. You can still do the resizing of the memory requests and limits as well, but yeah, it's a bit more complicated. Kubernetes kind of gives you this, this basic protection that it doesn't allow you to lower the memory below what the container is actually using at the time when you try to do the resizing. But yeah, with the memory, it's a bit more complicated than that, and I will get back to it a bit later. But now just to show you how Kubernetes kind of handles it. So let's edit the same pod again. And let's go back to the 800 milli-CPUs here. And let's try to lower the memory to 1 gigabyte only. Let's resize the pod. And let's check how the resize worked. So no resizing so far, still using 2 gigs of memory. Actually, it still says that the resize is in progress. So let's try to just update it and get the new status. And here we see that it says pod resizing progress failed. It's in error state. And the reason for that is because I tried to set the memory limit to this amazing number, which should be the 1 gigabyte. And yeah, it's using slightly more, so the desired size is below the actual usage. So that's why it didn't resize the container. So that's a bit more about the memory, which is a bit more tricky. Obviously, what I was showing in these simple demos was that I was resizing the pods using kubectl edit pod kind of manually, right? And in your production environment, you probably wouldn't want to be running with kubectl edit pods and using some resize sub-resources manually. It's probably not feasible if you have more than few pods. It's probably not very secure. It's easy to make some typos and so on. So in reality, you would probably use some tools to do the resizing for you. The most obvious one is the Kubernetes vertical pod autoscaler, which does have support for in-place pod resizing. And another option might be Open Cruise, which is, I think, incubating CNCF project, which also can help with things such as resizing, and it provides its own controllers and so on. And actually, we in Strimzi, we added support for the resizing as well for our Strimzi workloads. So you would usually use kind of tools like these to actually do the resizing and not run around with kubectl and kind of patch the resources on a pod-by-pod basis. But when you start using the tools like this, it's sometimes good to be able to kind of set some policies and establish some rules how the different applications handle the resizing. And that's why the container configurations also have now something called resize policies, where you can define directly in the container configuration how should the container behave when you try to resize the CPU or the memory. And basically you can say whether the container does support it without restart or whether restart is always needed. And you can define it separately for memory and CPU, because basically for the reasons I explained, that scaling the CPU, that's pretty simple and works pretty well. Scaling the memory, it's much harder without the restarts. So I, for that, just will apply slightly modified version of the deployment. So we will see a new pod created, and now we can try to edit the pod again. And what we can see here, so here are the resizing policies, where I basically tell Kubernetes that for CPU resizing, no restart is required. But for memory resizing, the container should restart. So let's now try to change the memory. Let's this time try to go to 3 gigs of memory, so we will increase it. So in theory, there should not be problems with the pod not having enough memory. But because we specified that a restart should happen, then here on the side, you can see that the pod was updated, but here you can see now it wasn't just in place, but there was a container restart. So one of the difference between editing the deployment and doing the resizing just with the enforcing restart through the policy is that you won't have a new rollout of the pod as you would have if you change the deployment, but instead the container would just restart inside the pod, which is something to keep in mind, because it can also impact things such as availability of your data, of your application services, and so on. Right, so let's continue a bit more. There are some more rules and limitations. So the first one is that you can today resize only CPU and memory. You cannot resize any other resources. Obviously, it's still a relatively new feature, so this might change in the future, but right now that's the state. You can't also change the quality of service classes. So if you have these guaranteed best effort, burstable quality of service classes, which are basically based on how you configure the resources, whether your requests and limits are the same or whether the limits are higher. And you can't kind of change it. So if you have the request and limit at the same value, you can't just increase the limit, because that would change it to the burstable class. Similarly, the resizing applies only to regular containers and sidecar containers. It doesn't apply to ephemeral containers, and it doesn't apply to init containers, which is quite obvious because in most cases they are not running once the pod is running. You also cannot remove the request or limit. So if you have your pod configured only with requests, you can change the request, but you can't just add limit in place without properly rolling the pod. I just briefly want to touch on how we did pod resizing in Strimzi. Strimzi is using its own pod management. We are using our own custom resources to manage the pod, so we are not using things such as deployments or stateful sets. And unfortunately, right now that means that the vertical pod autoscaler doesn't really work with the Strimzi pods. So to kind of allow us and our users to play with this and benefit with this, we actually build support for the in-place pod resizing directly in Strimzi. And the way it works is that users can, if they opt in for this feature, because it's not enabled by default, but if they opt in and enable it, they can basically just edit the custom resource and change the resources there, and Strimzi will automatically apply the changes to the pods and resize them in place if possible. Let's skip the demo of that for the sake of time, and let's talk a bit more about the practical side of things. And what I learned when trying to use it, again, mostly with Strimzi and Kafka, but I think a lot of the learnings apply to other applications as well. So is it as simple as it looked in the demos? Well, unsurprisingly, it's a bit more complicated, right? So the CPU resizing, that really works pretty fine almost everywhere. That's pretty straightforward, but the memory depends quite heavily on your application, how your application is designed, what's your application's architecture, but also what programming languages are you using, what runtime environments are you using, what frameworks, and so on. So you need to know these things, and Kafka is actually written in Java, which is probably one of the more challenging languages for this, but yeah, again, it's not completely different from other languages, so a lot of the stuff applies everywhere. So first thing, let's briefly touch on Java and the CPU. There's actually no major issue in the CPU resizing with Java, and actually one of the really interesting thing for a lot of Java applications is kind of the possibility to handle some startup CPU spikes, because a lot of the Java applications kind of need more CPU to kind of warm up when they are starting to kind of load all the classes and process them and so on. So the idea that you kind of, for example, start your application with 2 CPUs and then after it gets up and running, you kind of decrease the CPU to 500 milli-CPUs or something like that. It's pretty interesting. I know a lot of applications which would struggle to start with less than 1 CPU, but once started, they can easily run with 100 milli-CPUs without any problems. So that's an interesting feature. The memory, as I already explained, it's pretty complicated. So the main memory which Java applications are usually using is the Java heap memory. And it's basically configured through a minimal size of the Java heap and the maximal size of the Java heap, and it's configured when the application is starting. So either by the user directly, by some operator like Strimzi, or if nobody else specifies it, then Java will kind of check what's the available memory and set the limits on its own. So that's set at startup, and there's no way how to change it dynamically in some way. There are some plans and proposals how to improve this in Java, but right now that's the situation. And going back a bit to the Kubernetes protections, which they have for the memory resizing, like imagine you start the Java application and on the beginning and you say your maximum Java heap size is 5 gigabytes of memory. But right now, the application just started, it's not doing anything, and it's using only 1 gigabyte of memory. So actually, Kubernetes would let you resize the memory of the container from the original 5 gigabytes to 1.5 gigabytes, for example. But Java would not be aware of it, and a few minutes later, it decides to do something, allocate some memory, and it still lives with this 5 gigabyte limit. So you would suddenly run out of memory, and that's kind of Kubernetes give you some protection, but they don't really know about insides of the container and what runs there. Scaling Kafka on its own, it's even a bit more complicated than Java itself, because Kafka brokers are often pretty big pods with a lot of memory, so having Kafka brokers with 64 gigs of RAM, it's not really exceptional, but the way you typically run Kafka is that you will not have the Java heap use the whole memory. You would, for example, have the pod with 64 gigs of memory request. You would configure Java to use only 8 or 16 gigs of that memory, and you will kind of just reserve the memory for the disk page cache. The disk page cache, it's basically everything Kafka writes to the disk is the recent messages are stored in this cache. And when then Kafka needs to kind of read these messages and pass them to the consumers, then it doesn't have to kind of read from the disk. It just reads them from the cache if they are recent enough. And that gives us quite a lot of performance. But it also means that a lot of the memory is just the disk page cache. And the good news is that the disk page cache doesn't seem to have problem when you dynamically change the memory. So if I reserve more memory by increasing the request, the page cache will start using that memory. If I decrease it, then the memory will be gone, but the page cache can handle it. The bad thing is that the page cache in general uses any possible available memory, so it doesn't give you any kind of feedback loop. You don't know whether the memory is really the bottleneck. You don't know whether increasing the memory helps or whether decreasing the memory actually causes some performance issues. Kafka has one other workload. It's called Kafka Connect. And that's actually a bit more traditional Java workload, which doesn't write that much to this, doesn't rely on the page cache. And that's actually a bit easier to scale from the CPU perspective. The heap issues are still there. But yeah, it's one of the typical workloads where kind of the startup CPU stuff can be really useful. There are some infrastructure issues as well, which are really general and have not much to do specifically with Kafka or Java. But with Kafka or with many other big workloads, you often tend to use dedicated nodes, right? But if you have a dedicated node just for one application, there's actually not much value in scaling up or scaling down because, well, nothing else will use the capacity you free. So you won't really save any money. You won't really save any energy. You won't be any greener and so on. But you can take it even a step further. Because when we are running our Kubernetes clusters, one of the things we get from Kubernetes is this bin packing feature, right? It helps us to keep the utilization of our worker nodes high, and that's what we really want. We don't want to have thousands of worker nodes, each with 5% utilization. We want them to be really tightly packed with applications and having high utilization, because that means that, yeah, we are using what we are paying for. But that also means that there's less space for the applications to scale. So if you have this tightly packed node and then you try to increase the CPU or increase the memory of your pod, then it can very easily happen that the resizing will always be just deferred because there's no space on this node because there are other pods running, right? So that's something what can be a bit challenging as well, because it's a bit hard to predict whether your resizing request would end up in this deferred state or whether the resizing would actually happen. So we are going towards the end, so let's do a bit of conclusion. So I think the in-place resizing is a useful tool, but what's important to keep in mind is that it doesn't come for free, right? You need to kind of do some stuff to make sure you get some value out of it. And the first thing is that you have to know and respect your application. So if you are a pure operation person, just running someone else's application, and you have the idea, okay, I will start using this in-place pod resizing tomorrow, it's not that great because, yeah, maybe the applications can't handle it, right? So you need to first talk with application developers and see whether the applications can handle it or not. But maybe if you really want to use this, you should also plan a bit your architecture, your infrastructure, because maybe having large shared worker nodes would work better for you than having smaller dedicated nodes, because as I said, when you have dedicated node, there's not much point in resizing things. Maybe you want to also kind of mix some long-running pods and some short-running pods on the same worker node. So if you have some pods being these long-running Kafka brokers or databases, and then you mix it with some jobs which do just some processing for 1 minute, that kind of gives you the churn in the cluster so that you have always space to do the resizing. And finally, one thing to kind of a bit decide is whether you can rely on the in-place pod resizing or not, because in a way you are trading guaranteed scale for a guaranteed lack of disruptions, right? If you use the in-place resizing, you know that there won't be unnecessary disruptions to your applications, but you actually don't know for sure whether the application will scale or whether it will be deferred. So if you really need the performance from your application, maybe it's better to just kind of change the deployment or scale horizontally or use the vertical auto scaling, but without the in-place pod resizing, because then you know the pods will roll, they will be scheduled on a node which has capacity, and they will have the capacity then. They won't be sitting there as a deferred resizing. And that's pretty much it. So in the Strimzy community, we are always interested to work with users and improve the things, how Kafka clusters autoscale. So if you are a Strimzy user and are interested in this, feel free to get in touch with us on Slack, and we can try to improve these things and continue this journey. And otherwise, thanks for your attention. And I think we should have a few minutes for questions. So the first question, you mentioned memory request downsizing is forbidden. Is it possible to downsize the limits? It's not forbidden to downsize the memory requests or limits, but you can't make it smaller than the memory your application is currently using. So if your application is using 1 gig of memory, then you can't go below that, but you can, for example, change the memory request or limit from 5 gigs to 2 gigs, and Kubernetes would not necessarily mind. Whether the application can handle it or not, that's a different story. So I think that hopefully answers that. The next question is, what if pod process is partly in swap? Can memory be changed online? I actually didn't include it in the slide, and I would need to check the docs to be 100% sure, but I think if you are using swap, then you cannot use the in-place resizing at all. Can the restart policy be changed in the running pod? To be honest, that's a good question, and I never tried it, and I'm afraid I don't have the answer. I have it running there, so maybe we can try to change it later after the talk. When CPU count changes during runtime, how JVM and GC handles that regarding the number of threads? I think that a bit depends on how exactly is the JVM configured. I think in most configurations, there's now no direct relation to the number of cores it sees at startup and the number of threads it actually uses. So I don't think there's any major blocker right now. I think Golang had something similar around the number of CPU cores, but to be honest, I don't know how much it matters there these days or whether that's now irrelevant. The next question is, will it work for Java to set heap size with percentage and not XMX? So XMX, that's kind of the maximal limit for the heap size. You can also specify it as a percentage of the available memory, but it still applies that the percentage, it's kind of calculated on the beginning at the startup, and once you are running, it will not change. So if you change it from 100 gigs memory to from 10 gigs of memory to 100 gigs of memory, and you had the percentage set to 50%, it won't dynamically change from 5 gigs to 50 gigs. It will still be the initial thing. Does the app get any signal when C group limits change, or is the app expected to poll these manually? I don't think there is any signal, at least I'm not aware of one. And in the most applications I used it with, you actually don't need to really do much to understand that the C group limits change, because in Java with the memory you can't do much even programmatically, and with CPU, it just gets used. How does Strimzy in-place resize with other vertical autoscalers? So when Kafka pod is resized by some other application, it would not be immediately reverted by Strimzi. Most of the other resources would be automatically reverted, but not for pods, because we have there this kind of special mechanism where we track some special annotations which contain the hash of the revision of the pod configuration. And if you change it through some other means, either directly or through some other tooling, then we should not see it and we should not revert it. So that should not be a problem. Do you know if there's plans to support pod priorities and preemption in relation to deferred resizing? I think there is some support for it, but I will be completely honest with you, I didn't dig into it in a detail. Yeah, so integration with the priority classes, yeah, that's pretty much the same. I think there is some built-in support how these things are scheduled and how other things might be evicted, but I didn't kind of dive deep into that, so I can't comment much on it. What I can say is the different tools can also kind of combine these things. So what we, for example, have in Strimzi is you have to opt into the in-place resizing, but you can also say what Strimzi should do when the resizing is deferred. So in Strimzi, you can, for example, say that if the resizing was deferred, and Strimzi should actually roll the pod the old school traditional way and not just wait. So that's one of the options how to handle these things. And looks like that's all the questions. Thanks, everyone.
So I'd like to introduce Kim Sondrup. He will bring to our community a presentation, the state of Kubernetes on European sovereign clouds. So now, Kim, stage is yours.
Okay, it's just me. Thank you. We have a topic here that a lot of people is talking about for certain geopolitical reasons, maybe. Short about me, I'm Kim. I work for a company called Sondrup. I'm a platform engineer. So when we look at these providers we have in Europe, there can be many reasons. Like, of course, there's the title. But for some, it's like legal requirements. It can be pricing reasons. It can be strategic self-control of where your infrastructure is. It can be some, oh, what if this entire vendor goes down? That happens more and more in our time. But when we look at it, then no matter what reason that our management department say that we should do this, the problems we meet with building on them is kind of the same, and what we need to solve and what we need to run our clusters is kind of the same. So I'm going to leave the reasons here a bit behind and just look at the what and how a bit, and what they support. Quick overview of the vendors we're going to look at. We have Hesner, UpCloud, OVH Cloud, T-Cloud, Public, and Scaleway. The reason I added founded years in is to kind of showcase how long time they've been around. I still remember talking to some co-workers and saying, should we use Hesner for something? And they're like, oh, they're so cheap, they must be like some new startup. But they're not. They've been here for years. Most of them has a managed Kubernetes offering that we can use today. Hesner does not, but it's still kind of included here because there's so much community work around getting Kubernetes up and running, so we don't have to build that from scratch. Sure, you can run Kubernetes on anything where there is a computer, but we kind of want to have some managed or something taken care of because most of our job is most of our job in a different company is not to do the most core basic Kubernetes stuff and maintaining that. Yeah, I have to here because, again, it's a reason I see many places. But when people ever hear the argument, oh, let's use the thing we know, or why would you use that? They remember that is not a technical argument, and that is not a business decision. That is feelings and vibes. So let's see how we can provision something on what options we have out there today. So we're going to look at like the two main ones, Terraform or Tofu, because everyone has that in some regards. Cluster API, because everyone should have that, and when we look at the hyperscaler, they all have it. Then, of course, some quick mention of other options, because, again, we might care about the implementation, but the business just need a cluster running. For Terraform Tofu, all of the vendors have their own Terraform module they provide. All of them, except one, have in that module a resource to manage their managed cluster offering, with the exception of Hesner again, where it's community-driven. That, of course, can give some worry. That is community-driven if you build business stuff on top of it. Fine for a hobby project. The good thing is that when we look at the CABI, we suddenly see Hesner not by themselves, but a third-party vendor has made a supported offering. So you can give them money and then promise you support, which is important if you're going to build a business on it. When it comes to other vendors with cluster API, we have Scaleway. And then I did talk at KCD Helsinki with UpCloud. They're saying they have something on the way, with no firm dates. So it's the soon trademark kind of feature. But when I'm out to different conventions to talk to some of the vendors, the word is that, yeah, we're getting that request. We are looking at getting cluster API. For quick insight, kind of made the difference between doing stuff with the Terraform and the cluster API. Is that when you do Terraform, of course, you have, it's infrastructure as code, yeah, but you have to now maintain, your API now become Terraform. If you want to go and treat your cluster more like cattle, and just say, I can deploy a cluster like I deploy a pod, then Cluster API makes you able to use your GitHub flow and so much to your cluster management, so you don't need to have yet another process. Just for a quick show of hands, how many here has used Terraform before or Tofu? Oh, some. How many has used Cluster API? Yeah, okay, I thought so. Give it a look. If you ever had this, how do I automate my cluster creation? And it's hard to do that maybe with Terraform of templating that automatically, then give Cluster API a look. Other places, there is always the option, since everyone kind of have a Tofu Terraform provider, to wrap it in cross-plane and say, now you can use CIDs and your GitHub flow. Your mind may vary, so I will leave that to you to see if that fits for your business. Then Talos Linux is an option. You are introducing another vendor to it. They're good at what they do, but it's again, do they fit your needs? Kind of have to mention because they work so many places. Okay, we have a cluster running, that's cool, but we kind of need to use this. Cloud vendors, we need to authenticate with it. A big thing to, oh sorry, I jumped a slide there. We need to look at the different capabilities they have. Like what we're used to from the hyperscalers, a lot of stuff is built in. Like you can get everything from your hyperscaler and kind of build whatever you want on top of that and very much log in. And some features is not there in the cloud. A lot of them for the EU cloud vendors. So they just have to self-build some of it and self-host it. It's a trade-off always. Like if your strategy is doing multi-cloud vendors, then you might already be very interested in self-managing the stuff and instead of building on the cloud providers primitives, then building on your own primitives, your self-host. But again, it's important that this is driven by business need and not our technical joy of building cool stuff. Because it is a lot of work, and every time you have a capability with any kind of storage, you also need the disaster recovery time, all that fun stuff, and where's our trust boundaries? That's why OpenBAO is an example as a portable path, like with external secret operator, then suddenly you can have secrets everywhere. But then you need to manage a very highly privileged entity where if you're on the hyperscalers, you're like, oh, I'm just going to use their vault offering and don't think about backup of that, which you still kind of should, because if your cloud provider dies, you can have your business dying, but that's another subject. There we go to the identity. So we have three main things here when you pick a cloud vendor, and they have a Kubernetes offering. And that is single sign-on and identity provider is a very important feature for most businesses. We can't go around managing credentials and syncing it up by hand, so we like to have some kind of identity provider. Most of the big hyperscalers is also an identity provider built in. And in different degrees, very solid options. A lot of the EU cloud vendors are not really identity providers, they are just cloud. So that means it's very important for us that if we have an IDP, that be keycloak, intra-ID. You can even use one of the hyperscalers as your identity provider still if you want that. Nobody say you have to have your hosting the same place as you have your Office suite. Then we need to be able to sign into the web console like we used to. We would like to sign into the API, and we would like to sign into a Kubernetes API. The API, you might think that, but they do have tokens. I can just go in to the web interface and get a token, and now I can sign into the API. Yeah, but now you have another secret to manage and rotate and lifecycle manage. In most of the hyperscalers, you can go directly from sign-in page pop up and API is authenticated, or even better, which this is where there definitely need to be a risk cross for the EU vendors. You can go from machine token over to using and convert that to their own systems token, so you can directly call an API from your identity system as a machine. More slide on that later. From Kube API, what might surprise you is that getting a managed cluster suddenly means that you can't set Kube API's parameters. And in there we have what to authenticate with. So some of them you kind of get locked in that you cannot do the same thing again going from your identity system and signing into the Kube API. Big shout out to OVH Cloud for just directly exposing that flag on the Kube API. So you can set up your cluster to sign in with whatever. A big of a red flag for UpCloud, because their managed offering, you have to go in and create accounts to the Kube API for every user needs a unique account, or set up some kind of proxy. And I did ask them, and they're like, yeah, we know, roadmap soon. Then, of course, Scaleway and T-Cloud, they have integration with their own identity offering. Be wary again, how much can I go from my identity provider to their identity provider, and that kind of sort. I have looked a bit into it, but I don't want to say anything conclusive. I'm just saying, if they're not a good identity provider, then make sure your cluster is not bound to their login system. Then, of course, Hesna is like, it's a managed offering where you own the Kube API, you can do whatever, but it's, again, you suddenly can do whatever of bad things also. So it's not necessarily only good. It's nice to have managed. Here we get into what I have talked a bit with the API, but more spelled out, where we can go from machine to machine token. So concretely, when we say OIDC federated identity, or workload identity, or there's many names for it, it enables us to go from a service account and say, okay, I throw my service account over to we cannot really do it in the European cloud vendor, but let's say Azure. We throw it over to Azure and say, I have this service token. I would like to exchange that for a token that works in Azure. And then Azure can have policies that says, oh, when this issuer comes, I need to validate it. So it calls that little URL written down in the left corner. It calls the issuer and like .well-known, OpenID corporation, get the public key. We call that over HTTPS, so we trust it. We trust it's not manipulated. Because we have the public key, we can verify it. Then Azure be like, okay, I have a policy that says here is an Azure token. You can now call my API. No secrets to manage, no fancy rotation. You can just convert from one token to another. The same works, and here's a big one. If you have cluster API, or if you have Terraform, they also need a secret to call the API. Like one thing we use in ours is that our build pipelines, we can convert our token for the build job over to our cloud providers, giving us that, yeah, we kind of don't have to manage tokens anymore for Terraform views. So it's a big saver. Operation can be so fun to a degree, but there's no reason to add more of it just because. And not managing secret is a lot of saved operation. And then a lot of red, because yeah, the European cloud vendors just don't have it. They calling their API it's a secret management exercise. You can do some magic of trying to implement it yourself if you have a lot of keys, because you don't just need one key to the API when they don't have it. You need one for every level of authentication granularity your system needs. You could cheat a bit, but I hope there are some plugin to OpenBAO that can generate it for you and stuff, and then you only have one root secret that can make other secrets, but it's cumbersome. So that only makes sense at a certain scale, so there's this entire room from small to very big, where there's just a lot of manual work that Federation just will solve for you. Another thing that all the business need is that security comes down and say, we were hacked. Did we get affected? Let me just check time, good. And then you need audit logs. You need the audit logs from the API, the cloud vendor, hopefully. You need audit logs from the Kube API, hopefully. Not all of them are fully there with the Kube API stuff. Luckily, most of them are. Again, where is audit log sent is a parameter on the Kube API as a star parameter. So if the manager of it doesn't expose it, you can't set it. They also kind of dictate what granularity the audit log of Kube API is. You'll have to live with that, but that's the same actually of the hyperscaler. There is an equally bad feature all over the place there. So take that as a win, maybe. And then, of course, the cloud providers themselves. They have different where they end up these audit logs. That's less important from an audit perspective, more of a technical and a pricing. If you are price like log volume, because audit logs can be very data intensive. Do check into that. Like if you can do the multi-cloud strategy, then you might need your audit logs to get exported from their system or to some central, so you can do looking across. Then you need to look in like, okay, audit logs goes into their system, but can I get it out? Some of the hyperscalers also takes a pretty penny for that. So that's like, even if audit log is a free feature, then remember, logs are not And then in general observability, here I'm talking a bit against myself maybe in the fact that I'm talking about maybe being cloud agnostic, and if we pick a hosted offering for one of those cloud vendors we pick from, then we're kind of not a cloud agnostic, we keep buying into the ecosystem. But it's an important feature for the one that just like kind of pick a cloud, and we need to make that work, that we can have the managed offering of observability. It's a lot of data, it's a lot of backup, it's hard work. Managed offerings are nice. It's a bit here and there. I want to bring out scale rate a bit as a positive mention if you like a very integrated solution, that a lot of their products kind of integrate to send to that and like kind of have a shared ecosystem of the offering. Where the other one is more of we have an observability offering on the side and send data there. So it is depending on your need. Secret and native and portable. A bit what I hinted before, like the open bow for the start, versus, I'm saying open bow because it's a free offering. You can go out and buy any commercial offering that's equally fine. It's just solve the problem. There's just so many offers out there, so I'm going to pick the one that is most familiar to people, hopefully. And for those who don't know, OpenBow is the Vault fork. So some of the cloud vendors do have secret management, so they have to think back up and stuff. I want to give them a big criticism that since they don't have this federated identity I talked about before, anything that needs to talk to these secret managers that they have and get a secret need to have a secret to it. That I feel that kind of defeat the point, because then you're just moving the problem. It's cool if your pod needs 10 secrets, then you have one secret to work with. But it's less cool that you just, I need a secret to fetch my database secret. Nice. So a bit get that federated working if any cloud vendors end up looking at this. Of course, our cloud has no managed offering for this. Again, you can self-do it. You can go and buy something. There's also nothing stopping you from saying, my secret manager, I buy with a hyperscaler, and just use that. Like nothing stopping you from doing that. It's like or your identity provider, if they have a secret manager, there's nothing stopping you from doing that. It's just important that your secret is accessible and secure. Two things that is very hard to combine. DNS automation. We all want to give that thing to our users that they create a gateway and they set the host name and poof, DNS is set up correctly. That of course means that there needs to be some integration to that DNS provider. Luckily, they all have a very good show of features functionality. Some of them are community driven. Be wary of that. UpCloud have a partnership with Bunny. That is a European DNS CDN provider. Actually very cool, go check them out. But it's a planned partnership. They haven't shown how they're actually going to be and set up, so I can't really recommend or promise anything because I haven't seen it. Yeah, the rest, it works. It's there. It's one of the best lies because it's the most featureful. Cost allocation. Ooh, how many in here work with FinOps in like actively? Okay, it's a very important, I've been told. We have a FinOps guy in our team. I love him to death. It's a big hard thing to say. Okay, we have 10 teams deploying random pods all over the place, and because suddenly more nodes exist because they have more workloads. Which team made the cost? FinOps kind of closed that gap. We kind of need a tool for that. Most of these vendors have their own kind of, here's price cost and price estimate. You can see some projections. But what often ends up happening in companies like, how do I attribute to a team what they're costing us so they have an insight into that, and we can have an open conversation about it. For that, we need, of course, integration with some tool. You can get commercials offering. Go out and look at them if you want. They're not that much into different European vendors, but if you ask for companies, then they might get it. Open cost, when I started making this slide a while ago, there was only T-Cloud public. OVH Cloud has gotten, or added, like I think it's the last couple of months. Scaleway has gotten added in the source code, but there's no documentation. So we can ingest data about how is our workloads in our cluster and stuff. The problem is then, how much does this node cost, so we can actually get a number on it. For that, we need the cloud cost integration, where basically we can call the system and say, this node that runs here, what did it cost on my bill at the end of the month, or what they expect it to cost? And that is a sad site where there's not much feature. OVH Cloud has written that is coming in the open cost documentation. There's also a data format called Focus, if you want to look into solutions. That is basically a standardized industry format about how to price it and how do you identify what is a node and what is a VM and what does it cost. OVH Cloud has support for exporting that, so you might be able to just pick any vendor that has Focus support and then make it work with OVH Cloud in some degree. But it seems like a thing to have focus on again, since it's moving rather fast. The vendors are getting aware that these features are needed before looking into like the bigger cloud providers and taking some of their share. Okay, then a quick mention for the multi-cluster and hybrid. Sure, we can build something with a control cluster ourselves that has some in one cloud that can call the other's clouds APIs and deploy something. Again, it might not be a core business to do that, so there is options out there where it's like a managed offering that is built to exist in multiple clouds. And managed from one place, OVH Cloud has something, managed range of service, Scaleway, Kubernetes Cosmos. If that is your need, then they can be worth looking into. They also have some edge compute in it. But do be very sure that you're not logging yourself into something that doesn't really fulfill your needs because they only have the features they have, and it can be a bit slow turnaround to get a feature added. So build yourself. If you understand your primitive, how to do ingress in this cloud, how to do egress in this cloud, how to do a load balance traffic that comes in, how do I do authentication. You can kind of run any cloud vendor. It's kind of, you can standardize those and abstract those away from your applications. Like, yeah, there is no, if your application says, oh, I need Azure, then rethink that application. If it says I need Google, rethink that application. It should need primitives. It shouldn't need a specific product offering. So the comparison, like a lot of the hyperscalers have it, but they also have a very larger team and a head start. And the European vendors are getting there. I kind of hope to tour with this thing, maybe in a shorter format next year with see how many features they got and look how great we're doing in Europe and so many options. But let's see, like we know they're going to feature, but I hope they're going to solve some of the bigger problems that might block a bigger enterprise to get there. So, what can you do next? What the next thing you could do? Thinking capabilities, not products. So next time you have a user that comes and say, I need, I don't know, Grafana. Like, no, you don't need Grafana. You need a dashboard. Like, oh, I need Azure workload density. No, you need federated density. It's fine to use a product, and it's not necessarily the best business to go out and abstract everything away. It takes a lot of resources. But it's important when we do decision making and recommendation to leadership that we don't just recommend a product, but we talk more into what capabilities and what needs do we have that we need to support. Yeah, playing your machine identity story now. As Petr showed, it could be a big deal breaker that you suddenly, I have so many tokens I need to manage now. Figure out if you're big, you need either be very, very good at rotating tokens, or you need federated identities. And I know what I find more funny. Anything else. Verified, you can audit logs. Again, you might have legal requirements. It's no use. A little cheat for the audit logs, because there's rarely that requirement says that your cloud vendor need audit logs. They just need to say, you need audit log for actions. So if you can lock down to say nobody can call my cloud vendor's API, for example, they can only call my Kube API and to manage everything with like cross-plane or cluster API or something, and then do audit log on that, then you have an audit log bar that you could argue, and probably pass, that is your control from a legislation perspective. GitOps is your portability layer. Or I did a lot of talk there about identity and how to sign into a cluster and stuff. But the more thing you can do in GitOps, the less you have to sign into a cluster. You can't probably not get totally away from doing that. Like our operations team would be very sad if they had to debug with GitOps. But the more work you put in there, the less you have to think about all these different paths of authentication and stuff. You can more think is like, what is our promotion flow of config? Yeah, validate your cost model. Like, again, if you suddenly use a cloud vendor and the team starts to use a lot of resources, be sure that you know how to address it. Because there is not that many products out there. You can't just hope for it to be there and be functional as you can with a lot of the hyperscalers, where there's a product for everything out there. Yeah, do it. Try it. Do it as a work thing. Do it as a home hobby thing. I can say some of them price is easy motivator for development workloads, doing testing. Some of them also sell with very like faster single core CPU performance because they have some different SKUs they're aiming at. So if your developers complain about build time, then especially give a look. And then of course GPUs, if you're in that use case where it's like, oh, you can't get more GPUs, they're too pricey, then especially look at the multiple cloud vendors, because a lot of these also sell GPU resources. Then yeah, in short, the ecosystem is there. There are some gaps, but it's there. Like, you can get started now. You can get a solid enterprise offering. Yeah, questions? And there we see. Okay, so OpenBar, how do we validate sovereignty? So the way I often view it is that there is no loyalty or country in source code. Like, code in itself is not important in that aspect. What is important is the build infrastructure and it's the people to maintain it. So in a hypothetical world, where for whatever reason, we suddenly need to, right now it's probably built on some shared infrastructure on some American server somewhere. But let's say that it suddenly is cut and we now need to build it in Europe. Is the people enough available that can do that and have that skill, have that knowledge? Then yes, it's sovereign. Can we, like, if you want to make it sovereign for start, then have a mirror of the source code and have a mirror of the install binaries. And then have a written down plan of, these people are from Europe and they're going to be we're going to try and get them as maintainers for some way if the worst case happens. And boom, you have a backup plan. Like, source code is not loyal. It's just run wherever it runs. So yeah, that's the major one. Where's the build infrastructure and can you replicate it? I think that was it. Thank you very much for listening.
domov? Ešte počkáme, o tých 25 začneme presne. Ďakujem. Really? No one has a catch for the sentence, CDN? Oh, well. Here's my story of So, hello, I'd like to introduce Tomas Boros. He has his own project, Edge CDN, and he will introduce you how he looks on CDN by his own eyes. So, stage is yours.
This one's okay. This one's working as well. Okay, thank you very much. So I'm going to start my presentation with this statement. If you were here on the first day at the keynote speech, it was mentioned that Kubernetes is a platform for building platforms, and I very much agree with that. If you just look at the broad ecosystem of the CNCF landscape, you have amazing amount of applications and orchestrating platforms to use on top of Kubernetes. If you want to run PostgreSQL databases, you can take the Cloud Native PG operator, and you can pretty much easily manage PostgreSQL clusters on Kubernetes. If you want to manage your rollouts, your applications, or even rollouts application remotely from a single point, you can use Argo CD. If you want to manage Kafkas, we had just a talk about that recently. You can use Streamzy, and even you can provision cloud resources with Crossplane. Although you can end up in a situation where I was at one point, where none of those tools actually fit my use case. So I decided to build my own operator. And how do you do an operator? A controller, it's pretty easy. You have to define a few CRDs. You build your controllers, and you hope you know what you're doing, and it's actually doing what you're supposed to do. So a little bit about myself. My name is Tomas Boros. I'm a DevOps engineer. I work for a small Dublin-based company for several years now. I have a background in research. I did some research on CDNs and video streaming, especially on MPEG Dash. And I used to work as an external contractor for Slovak Telecom and TIMETABLE Czech Republic. And I was in charge of building the CDN platform for the Magio Go OTT platform and live TV. Just a side note, this platform is quite huge, running around on 80 servers, and currently is reaching around 3 terabits per second in an aggregated maximum throughput around larger events like football or hockey matches. And since I no longer work on the project, I decided I'm going to join my know-how and my expertise on CDNs and DevOps. And I decided I'm going to build a CDN on my own. And of course, the obvious choice was Kubernetes. So just a few slides on what a CDN is. CDN is basically a distributed network of servers distributed globally around the globe, and it helps you to deliver the content to your users faster and more efficiently. It reduces latency to your origin servers and overall improves the user experience, and it is doing by storing a copy of your content from the origin server. So for instance, if you have users in this use case from US, downloading an image, a video, or whatever content from your origin, the user is not sent to the origin itself, but is sent to the closest cache. And if the cache contains the given content, it delivers it to the client. If it does not, it will first fetch it from the upstream, and it will honor the cache control headers from the HTTP response and will cache it accordingly and then serve it to the clients. So in such use case, if you have millions of users requesting the same content, all the content will be served from a cache itself, so you are essentially reducing the load on your origin massively. And how the actual routing is working in a CDN. How do you decide where to send your users. So in most of the cases, the redirection is DNS-based. You ideally want your DNS to be behind an unicast IP address, and this works in a way that whenever a request comes in, the DNS server looks up your IP address, and it tries to make a perfect decision based on your IP address, and will redirect you to the closest DNS server by sending you an A request on a AAA request response, to the cache with the IP address of the cache which is closest to you. There are also some alternatives. You can also use HTTP Anycast. So essentially, you are just redirected to any of the cache servers directly with an HTTP Anycast IP address. This has some drawbacks, and at some point, also 302 redirection methods were used as well. I would say it's not really common to use that anymore. That works in a way that first you send your HTTP request to one of the routers, and the router will send you a 302 redirect to the closest cache. This has a bit of an advantage because you can take into consideration way many more parameters how to do the routing decision. For instance, the user agent, the content itself you are requesting, although it has an extra round-trip time because first you have to do an HTTP request to a router, and then you do another request to your cache itself. And why did I decide to build it on Kubernetes? First of all, because I worked with Kubernetes for a couple of years, and I know the platform well. Kubernetes itself offers a very reactive control plane thanks to the Kubernetes API. The tooling is great, and you can easily extend the API. The solution itself is ingress-based, and it has a first-class support for certificates with Cert Manager, and there is a DNS in Kubernetes available. You all know the core DNS, which is actually pretty easily extensible, and I will get into details of that. And how the control plane works basically in Kubernetes. In the end, everything in Kubernetes is essentially a controller, and what the controller does, it is basically just continuously compares the desired state to the current state. So whenever there is a change to a given resource, an event is fired in one of the components, and the reconcile loop will try to get that resource to a desired state. So for instance, if you create a deployment, the kube, you do a simple kubectl apply of whatever YAML file specifying a deployment, it will be picked up by the kube control manager. The kube control manager basically will seize this information and will create a replica set that is going to be picked up by the kube control manager again, and then it creates a few pods. The pods are then picked up by the scheduler. The scheduler chooses the right node to schedule the pod on, and whenever it found a suitable node, the kubebot locally on the node itself will pick this information up and start a container, either with containerd or some other containerization system. All right, so as I mentioned, you can extend the base functionality of Kubernetes by custom controllers. So you have to define those CRDs, and those controllers are basically then just reading the Kubernetes API. They use an email stream through informers. So every time there is a create, update, or delete event happening, the reconcile happens, and your controller basically is responsible for getting the resource into a desired state. So for this tool chain, I decided to use KubeBuilder. It's a Golang-based tool chain for building Kubernetes controllers. I've included a link down there if you're interested to check it out. And for distributing the configuration over the platform itself, I decided to go with Argo CD. It supports a multi-cluster architecture, which means you can manage multiple Argo CD clusters from a single central point. So a little bit of insights. So basically, every single node in this CDN platform is a Kubernetes cluster. So the control plane runs in the middle. That is responsible for configuring the whole platform. And every single cache or DNS server basically is a separate kube cluster, which is onboarded to the Argo CD on the control plane. And you can annotate and define a few labels on those specified clusters. So you can give certain roles to those clusters. In this way, you can decide whether this node is going to be a caching node or whether this node is going to be a DNS node. So these are the CRDs which I have defined. Very few ones. I will go to the next slide because there's more details. So I have a location. I'll have a location CRD which identifies the endpoints. It manages node groups, and it defines also the geo routing. Each and every location, basically, it could be, for instance, Prague or Bratislava or Europe or whatever. And you can define multiple you can define multiple nodes in a single location, and you can also specify which geotext should the CDN route to. You can define prefix list. This is useful if you eventually would like to use any static routing, or this is also a sort of a preparation for an eventual BGP listener. So for instance, if you want to place a cache into the network of a specific ISP, and you exactly know which prefixes are do belong to this ISP based on ASN number or the prefix list, you can low feed those prefixes into the routing system as well. The project is simply just a UI feature for grouping customers to enable multi-tenancy and projects. The services itself are the services that you roll out. Here you specify basically the domain names, the upstreams, what kind of caching mechanisms, what kind of cache control. We will get into details as well. And you can define some zones. Zones are basically delegated subzones, DNS zones. So you can onboard your own domain. So the platform itself works with a predefined domain, but at the same time, you can specify an external domain which you can delegate with NS records to the CDN platform. So in action, if you create a service resource, I have to mention that this is not a standard service, which you know in Kubernetes, but this is a services.infrastructure.hdnx.com resource. If you create a resource like this, the controller on the control plane picks it up. It creates an application set, and the application set ensures that this service is basically distributed to all the endpoints over your CDN cluster, and it also handles the certificate management. Whenever this service gets created on a cache node, the controller runs there as well, but in a slightly different configuration. So it picks up the service. It creates a service which will point to an external service which you have configured as an upstream, and will create an ingress with a bunch of custom annotations. So it can also not just forward the request to your upstream, but at the same time also cache the content. I would like to add that the platform also supports S3 origin types, and currently it is solved by just simply deploying an Nginx S3 gateway pod, which is essentially can connect to an S3 bucket, and you can use it as an upstream for your CDN. And whenever a location or a service is created on a DNS node, when a location is created, it is loaded into core DNS, and a probe is created for doing health checks, and the service just basically just resides there, and no extraction are taken because it is only needed by the core DNS itself, so it can respond to those requests. Okay, this is how the service looks like. You can specify the caching layer. In this case, it's an SSD cache. The domain name, basically, which core DNS will respond to, and also the Nginx ingresses will respond to, and the static origin configured. In this case, it's testorigin.dbiotech.sk, which is my testing website, basically, for this project. And you can define WAF and then a few other things. So the next part was basically the core DNS. I had to make sure that the core DNS can work with those CRDs. So instead of trying to generate the correct configuration and reload core DNS every time, I decided to build a plugin. And the plugin is, I would say, pretty mature and pretty cool, and it can do all sorts of things. It can route your request based on static prefixes. It can do geo-lookup as a fallback if there are no prefix configured. It can, whenever it finds a specific location where the clients should be redirected, and there are multiple servers available in the given location, then it does consistent hashing. So it makes sure that for the same domain name, you always end up on the same server just to make sure your cache hit miss ratio is as high as possible. Whenever there are no nodes in a given location, it can do fallback routing. So for instance, if there are no nodes available in Bratislava, you can fallback the request to Prague, for instance. And the two cool features which I really like, you can also specify for those specs Prometheus alerts. So let's say you have 5 servers in a region and your maximum throughput capacity is 100 gigabits. And whenever the location is getting close to 80 gigabits, you can fire an alert that please do not send new requests to this location anymore because I might get into congestion. And of course, it is doing active health checks. Yeah, so these are a visual representation of those routing features. On the right side, it's simply just routes to BTS, which is Bratislava, just routes the request based on geo-lookup tags. The one on the bottom is basically the same defined for Czech Republic, although the nodes are unhealthy, so it has a fallback specified to Slovakia, so it goes back to BTS. And on the left side, it has a nodes server running in Frankfurt where I have defined a random prefix. So whenever there is a request with that prefix coming in, then it will be routed to Frankfurt. OK, so these are the CRDs which coordinates work with. The prefix list on the left. I'm not sure if the one on the right is readable, but I can show you later on. On Argo City, how does it look like? But basically, I can define the geo-lookup attributes, and I can allocate a certain weight to each geo-lookup attribute. Here in this case, I have EU and Africa set with a weight 1,000. And so basically, on routing decisions, the request goes through all these geotags and all these locations. And whenever you get the highest weight, you will be redirected to that node. If you end up in a situation where there are multiple locations candidates with the same weight, then you can still do a weighted round robin, basically. OK, and to make sure everything is dynamic and fast in this platform, the core DNS and the health checker components are basically using Kubernetes informers. The informers are treated as an event stream. So in the background, what an informer does, it connects to the Kubernetes API, does the initial get of all the resources, and then starts watching all the changes from that point. So Kubernetes snapshots and versions the state of every single resource. So essentially, you are ended up with an event stream, and whenever there is a change, the changes are automatically reflected in your application itself, without having to reconfigure having to reload the application. And there is also one note which I need to add. If you have many, many, many resources on your Kubernetes API, to fill the cache takes some time. So you can check if the event stream is basically already up to date with whatever you have in the Kubernetes API. And if it's up to date, then it will start serving requests, and that is solved by hooking in the readiness probe basically into this component. OK, and on the caching itself, it is built, I would say, unfortunately, still on Nginx in Res. I know it's deprecated already. It does support multiple tiers, so you can have multiple node types in a single location. You can have SSD servers for your stairs, RAM disks, etc. You can configure certain key modifiers. Like if you look at the example here, it's the image.jpg with a query param with 124 and with 2048 will essentially give you a different result. So you have to specify that key as a, you have to whitelist that key, and it will be stored in your cache key, basically. As I mentioned already, it supports S3 origins. And if you want to serve private content, you can enable the URL signatures. That is pretty much standard with S3 and whatever other sort of CDNs, if you have worked with, to access a certain content, you have to sign the URL. If you sign the URL and the URL is valid, you will then get a session token, And whenever then you request subsequent request with the session token, you will be authorized, and the session token is eventually renewed on 60% of the validity of the lifetime. And I was playing around a bit with a bit of performance. I just already mentioning here that the platform is compatible with SRIOV. SRIOV stands for Single Root I/O Virtualization, which is basically where you need a network interface card, which has this feature. And with what it can do, basically you can get a virtual function for your physical interface and put it into the Nginx pod itself. And this way you are going to bypass the CNI itself. So you should not consume unnecessary CPU resources on traffic routing and the networking management. And eventually, what's going to be the future of this project, since Ingress Nginx is deprecated, probably I will write my own controller for a different caching engine. I haven't decided that yet on which one. Probably I will go with ng. It's a fork of Nginx pre-F5 acquisition because it contains a lot more and many modules that are basically now behind a paywall on F5. And of course, it has a very basic analytics and monitoring standard on Elastics on the Grafana Prometheus stack, and the logging is basically done with event streaming. So all the nodes are shipping their logs to the central point, and I'm running basically a simple stream processing application that basically aggregates the logs, and we get very basic statistics, how many megabytes or gigabytes were uploaded, downloaded for a certain service, so we can see what our actual usage and what our actual savings are. All right, I will continue on the demo from here. I do have some backup videos just in case, because you know demos always go wrong when you are doing it live. Okay, so this is how the parent currently looks like. The portal is actually live, and you can give it a try. It's running at portal.demo.hcnx.com. Feel free to sign up. Feel free to test it out. The demo environment, unfortunately, only is running 2 locations because of the cloud costs, of course, but it's just more than enough for demo purposes. So it is OIDC enabled. Once I log in, I can look up the available locations. As I mentioned, I have one in Frankfurt, which is healthy. And there is one node specified with this IP address, and it has a single node group. And in New York City, I have 2 node groups, 2 nodes, and this is the geolookup config, which is configured for this service, for this location, sorry. So Antarctica, how to say in English? And North America, Oceania, South America, and Asia is basically routed to this location. I have the defined prefix list. So whenever there is a request coming in from this prefix, the request will be routed, in this case, to New York City. And you can also define some zones, as I mentioned, and also the customers can onboard their own zones by specifying it on the project dashboard. So now I'll do a quick demo. If I open this project, I'm going to create a new service. I'm going to call it KCD. It will be a static origin type. I have to set an upstream URL. And for that, I'm going to use this test origin, which I mentioned in the presentation as well. I'm going to set it to an SSD caching tier. I'm not going to set any query params. I'm not going to set any paths because I just want to basically forward to the upstream everything under /. And I submit it. Once submitted, it gets created on the Kubernetes control plane, and the certificates start issuing. And if I look into the Argo CD endpoint, you can see that there is already an HTTP challenge exposed for the certificate, one thing I need to add that getting the HTTP-based certificate issuance was a bit tricky here, because in a CDN you can essentially end up on any of the nodes. So you don't end up on the node where the service itself is configured. So the controller is managing that whenever you get the token from Acme, from the cert manager, which you need to expose, the challenge is copied to each and every node around the CDN cluster, basically. So this way, the token is exposed everywhere. So whenever the request or whenever the challenge request is coming from US or EU or whatever else, you will always get the desired token. And this way, hopefully, the certificate will get issued. Yes, the certificate is already valid, and we can see that the platform is configured, and there is a domain name which I was assigned. And if you open DNS checker, let's wait a bit. If you open DNS checker and you test if the domain resolves, you will see that request coming from the US ends up on this server, and request coming from Europe ends up on a different server. So the core DNS, the domain names, the ingress, and everything was configured literally probably under a minute, including the certificate issuance. So if I would like to further do some tests, and then I also want to show you that it actually works. So this is already the test website, which is now proxied through the CDN service. And of course, I have some pictures of cats. That's something you always need. And if I should have done this. Hold on. I'm going to do this way first. So I'm open a different site. And you see at random content, you will see in the status that it's a cache miss, because this is the first time I'm accessing this website. So right now, if I do a refresh, my content is coming from the cache itself, and it's a cache hit because it was already stored in the cache itself. And one more thing I want to show you. On the right side, I have the logs from core DNS running, and I have a nice script which I can show you the routing, how does it work. I'm testing it with a different domain, which is onboarded in this platform as well. So if I do this test, it will just simply do NS lookups against this domain name, and will basically print out on your screen what is the response. So I did a request to cdn.tbotech.sk, and I received an IP address of 74.220.31.138, which is the one running in Frankfurt. And why did it happen? Is it readable on the site? Or should I make it bigger? Yeah. So as you can see, the geo lookup kicked in. There was a question for this domain name, and based on the geo attributes, the request was assigned with the score of 1,000 for Frankfurt C1, and there is a server running in Frankfurt C1, so I got this response. In the next test, I mentioned to you that you can specify some prefixes. DNS actually has an extension which is called eDNS0 subnet. It is because if you use a resolver, for instance, 8.8.8.8, or whatever else, that which can, even though you are based in Prague right now, the resolver can run somewhere in Germany or wherever. So what you can do is basically the resolver can inject the source IP where the resolver received the request itself, and can pass that information down to your resolver. So if I do the very same dig command, although I specify this plus subnet, if I specify this subnet as well, that I'm mimicking that basically I'm coming from this source IP, and the core DNS will first look into the DNS subnet. If that's present, it will route based on that. If it's not present, then we'll fall back to the source IP it received the request from. So in this case, you can see that the v4 static prefix was matched, and I'm routed to New York City. And in the last test, first I'm going to kill my pods in Frankfurt. The pods are killed. And within a couple of seconds, if I manage to catch that, I received an update, which means that the health check failed. And my health checker patched the CRD with this information that the health check, that the node is down, and that information, thanks to the informers, were automatically reflected in the core DNS configuration itself on the fly. So here you can see I was supposed to be routed to Frankfurt, although node is not healthy, and there are no healthy nodes from this location anymore, so it's doing a fallback routing to New York City. So I ended up being redirected to New York City. Of course, in real life, this is not really a useful use case. You would rather route somewhere closer, but I only had 2 nodes, so I don't have any choice. But sometime later, whenever the pod comes up, the pod should be healthy again. So if I do the very same request, now I'm getting routed to Frankfurt because the pods are alive again. And yes, I think pretty much that's it. I'm glad that the demo went well. And let me just finish the few more slides I have left. Yeah, I just want to do a quick summary, basically. So this is more or less still a hobby project. It's not really deployed anywhere in production. I managed to build a full CDN capability based on top of Kubernetes. I have right now a POC deployed at Lyrid.io. They are a small Heroku alternative, mostly operating in Asia. They were interested in the project itself, so they have a POC, but currently no actual production running. And the portal which I showed you, which is present on this website, I will be happy if you give it a try. And of course, if you are interested in the project or would like to take a look, would like to collaborate, or if you have an interesting use case or you work for someone where you think a CDN would be suitable, I'm very open to collaboration. And you can find me here, and that's it. Thank you. All right, so the first question is, can you explain again how do you match packets source IP address with a prefix list and the EU-US stack? Okay, so there is a chain of routing, basically. First of all, the source, the prefix lists have higher priority than the geo-lookup. So if a packet comes in and there is a prefix defined for that IP address, then it will be routed to that location. If there is no prefix, then it will fall back to geo-lookup. Okay, next time, what about gateway API? Are you planning to move from Ingress? Yes, I'm planning to move from Ingress, but probably not to gateway API, but as I mentioned, probably to writing my own controller based on NG or Varnish or other caching engine. Technically, yes, but whenever, if I would get to a point where that CDN could start growing, I mentioned that I'm planning to add a BGP listener, which you could do that for me. So it would just run as a listener and ingest the prefixes which the specific ISP wants to route the prefixes to. And those prefixes just simply will be copied over to the Kubernetes API, and then the core DNS will itself do the routing. And next one, what would be the main motivation to run my own CDN? Running your own CDN makes sense only at a certain point, and I would say you need to be consistently at least streaming or delivering content at least at 10 gigabits per second. Otherwise, the cost will never, it will be always cheaper to run a managed solution, basically. And if you are an ISP and you have an IPTV, the use case like Slovak Telekom and TIMETABLE Czech, they really do have a use case for a CDN. Just for information, I did run the numbers based on the traffic they are delivering daily. If they would use Cloudflare or other solutions with the standard pricing, so they could probably negotiate better prices, but I did the numbers with the standard prices, they would be paying around 100K per day for the CDN. Do you have an example? I do have an example, but I cannot show you here. If you go back, if you find me on the socials, I have a YouTube channel and I have a video on that, how do I configure that. Timescale DB is not used for access logs. Timescale DB is only used for the aggregated data, for calculating basically the received and sent bytes over time. Well, I'm not running bare metal right now. And honestly, I probably would not use any, I would probably just use a simple host path. And I would probably use a cache in RAM disk itself if there's enough storage, and probably do an LV cache to a larger storage and SSD underneath. Yes, this was mentioned. I do rely on EDNS client subnet, and I don't really think there's anything better than that, unfortunately. And as I mentioned, if there is no EDNS client subnet available in the request itself, then it falls back to the source IP of the DNS request itself. Yeah, the next question. This is a very good question. I can actually, it is very hard to find a hyperscaler or a hosted CDN, a hosted Kubernetes solution which you can provide you with a load balancer which preserves the client IP. So Azure and AWS can do that because they have their own funky networking stack. But for instance, I'm running on Civo, and I've talked to several engineers at Civo asking if they can preserve the source IP address of the DNS request on UDP, and unfortunately they cannot. So I had to fall back by running a VM next to this Kubernetes cluster running Docker with a public IP.
Thank you, Tomas. So we will not stay, except of course me, Tomas will not stay more between you and the lunch. So please enjoy your lunch. Thank you, Tomas, for your nice presentation. It was very nice topic, and as you saw, the questions was so interesting and a lot of. So catch the Tomas, don't let him breathe. Outside there is a lunch for you. Thank you so much. I bet you all enjoyed the lunch. If not, I'm sorry that. But two guys, one David Pech and one Petr Rais, came you to present, really present the feel, the breeze. So there are first rows and they are empty. So everybody like to take care of their health and don't like to freeze, I bet. So yeah, from my side it's all, and stage is yours.
Hello. So we are very glad that you made some time after the lunch, to be educated, of course. And we also thought like how to approach this session, because we were going to talk about some sustainability topics. So I am David. This is Petr.
Hello.
And we would like to discuss how did you get here, right?
Yeah.
So the thing is that depending on the level, let's say, of altitude of your transportation, you can get a very different experience and number of kilograms of dioxide that you produced. So what I would like to highlight that if there is anyone who use a plane, this is the worst thing that you can do from Bratislava for sure, right? Even though the time probably is not that bad, but still. You could have taken a bus, but from Brno, typically. I guess that from Bratislava is not that convenient, so we are comparing slightly pears to apples, right? Or, in my case, I took a train from Ostrava, which is, as you can see, quite green. Perfect, right? Maybe you are just a Prague person, so you took a subway, why not? Or you could have walked. Is there anyone walking from Bratislava to Prague over here? No? Surprisingly. Okay. I really wondered why there is 0 kilograms for this one, and the thing is that for basically animals, humans, it's not measured. So there is not let's say 0 exhales, but it's not measured. In fact, when I discussed it with Claude, he said something like, okay, but if you are to walk about 330 kilometers, you would consume the food an equivalent for 20 kilograms of exhales. So if you need to digest anything, basically this would add up. But the walking itself is completely fine. You are some kind of exemption, right? But let's get maybe to something more technical, and this is what the talk is going to be about. If you are running some pod that is idle and that is consuming 5 watts for a year's consumption, you could get also to these numbers, meaning of one single trip around, Prague. Which is kind of frightening, meaning that if you imagine this and if you really try to untangle it from there, this means basically that if we would save a few pods in each of our clusters, we might significantly save, right? So it's not just about the money perspective, it's also about being green. One thing that I will remind you again later on is that how the calculation is being done. So of course, if you are using a bus, an airplane, etc., the calculation is quite obvious. You just take the fuel, right? And it's some emission factor. But if you are using electricity, it's very different. So for each basically state or region, there is some coefficient that basically says, okay, for the Czech Republic, you get some number. So you can basically do some sort of estimation and some calculation how much of the consumption is being equivalent to how many exhaust gases. Thank you. So just a reminder why this is important, right? We have an example of Meta basically needed to cancel its plans to have another data center in the Netherlands. The motivation for it was that, in my company, we also had a Netherlands data center. And when we wanted to expand it, a year from there, we don't have it there anymore because we are not allowed to get more power for some reasons. And this is just an example how demanding that data center is. So, it's really a huge investment that probably can correlate to some car, automotive factory, etc. So a lot of land also involved. You can see some politicians discussing it in Netherlands and having some motions against it. So it's really not obvious if we will be able to build these data centers, maybe in the same way that we have been trying to build some power plants lately, and some people are opposing it. So something like this is definitely going to be a problem, and we cannot take that, some large company is going to build yet another data center as a granted thing, right? So what we are trying here to present or address. First thing is that we, of course, are Kubernetes people, right? So we would like to highlight that there are some distributions that can be significantly smaller that you can get by the default Kubernetes setup, having Freenode on the master, etcd, and like all that jazz. For example, there is K0s. This is the pronunciation that hopefully is correct in my, in my mouth. So you don't have an etcd, you, for example, have SQLite behind the scenes as a database, you have just a single node cluster. So even for a very small environment, this is the way how you can have a Kubernetes on there, and from Kubernetes you can have Argo CD and a lot of stuff behind it, right? So here is some explanation that even on Raspberry Pis, you can run it. For this presentation, we've tried to do also Raspberry version 3, but unfortunately like 1 GB of memory, that was enough, but the speed of the SSD, sorry, not SSD, but the flash drive was too low, so we needed to switch. So probably this is, let's say, some practical example if you are doing like some kernel stuff, optimizations over there, that with Raspberry Pis you can run the Linux pretty effectively, you can run K0s as a distribution on top of it, and you basically have just a regular operation system, not a big deal, right? Very similar to what you have on your regular servers, which I think is very different because typically when we are discussing some edge cases and IoT things, the operation system, the distributions you get is super limited. But you can see with this that it really resembles a regular computer, not a big deal. For the installation, we will showcase it later on, but you have some very simple script how to do it. You just connect it to internet and let all the files being downloaded if you like. So this is definitely a way how you can build, of course, your home lab, but of course, this is extendable to some factory design. Imagine that if you are in a scenario, if the company would like to have some, let's say, detached offices, etc., and they are deciding if they need to buy a rack there with a regular 1U server, or maybe we can go with something lighter. So this is really your chance to get Kubernetes, there, but also something lighter from the sustainability perspective. One trick that you might use is that Argo CD, in fact, does not need to cover just the cluster it is installed in run. So basically, you can control through the Argo CD and use it as some kind of a control plane to other clusters. And this is basically the example that we have over here. So the Argo CD is running on the cluster on the machine, and on the Raspberry Pi, there is just the Kubernetes control plane through K0s, and Argo CD syncs to it. Again, we will showcase on the demonstration. There is just one parameter, so you can have multiple clusters being configured in Argo CD settings, and basically the sync works, over the network as it would work locally, out of the box, not a big deal, right? What is also interesting that there is a primitive in Argo CD like CRD that is called application sets. Not sure if you are familiar, but basically you can have some multiplication, meaning that you say, okay, for these 5 hosts, or clusters in our case, these 5 Raspberry Pis, I would like to have all the same versions, of these manifests. And it's very easy then to control, 10 devices instead of 2. You don't need to do anything manually, you just work with the application set. It can also have a connection to Git, if you like. A lot of cool things over there. But the main idea is that basically you have a central, we call it HQ, like the headquarters cluster, and then you sync to the edge location from over there. Again, we are not showcasing like anything edge specific. We are really having a regular, let's say, operation system and things around it. What I would like to highlight is that people typically think that, Argo CD, for example, for it's to work properly, it needs to be always online, connected, etc. It's really not so, right? So Kubernetes itself has a lot of checks and balances, let's call it like this, that it can recover from pod restart, pod failure. It can scale back some deployment if you have some problems. So a lot of scenarios can be covered just by the Kubernetes itself, and you don't need Argo CD there. So just like a reminder that even if you have some location that, for example, keeps switching on and off, that has unstable internet connection or anything in this direction, you still can control it remotely. Of course, there might be some gaps in your logging, for example, in your metrics, but do you really care if we are in that detached office, home lab scenario? Typically, you don't. So the scalability and the ease of management is definitely something that you can leverage out of this example. One CNCF project that we would like to highlight over here is the project Kepler. Is there anyone that has already used it? No? Okay, perfect. There are people over there. So, you know, it wouldn't be a CNCF project if there would not be eBPF, like somewhere in behind, but not really. What does it do? Basically, it is trying to calculate and bring the power consumption to the units that we know, and we can work with them on our company level. What do I mean by it? It basically says, on this node, we have this input power, we have this consumption, CPUs are distributed across running pods like this. So it is trying to calculate idle power and the dynamic power, it calls it, meaning that you are able to get the numbers, how much power consumption is your namespace X using. So, of course, this is some estimation. The estimation is mostly based on some ratios between the CPU usages. So, if it also tries to bundle in the memory, drives, and a lot of other stuffs, because even if the server is idle, it is consuming something. There is a table for the comparison, so you can see what is the idle consumption, what could be the consumption in load for different types of hardware, because we think that people typically as we are getting detached from the hardware, people typically don't know. So this is why we have also the live example over here, and some questions, of course, around it later on. So basically, the project Kepler can give you some introspection, some metrics around these. They may be too complicated, but the baseline is that you can measure the consumption on the namespace level, the very same as, for example, you would measure the number of CPUs and other basic stuff. The project is currently in the sandbox, if I'm not mistaken. And of course, one very interesting thing that is added recently is the GPU power consumption, which is of course going to be huge. As you can see, those GPUs probably will be significantly or several times more consuming than the entire else of your PC. There are several machines that we wanted to showcase, if we may. Thank you. So those are the better GPUs, but they are not for gaming these days. They are for the AI inference and AI training. So these are called accelerators. And just to showcase everything, I don't understand these numbers much technically, to be honest. Let's call it a supercomputer, on a chip, something like this. And the loads that there are really frightening. Something like this basically could maybe heat your small house or a cabin if you'll have something like this. But we are getting in even higher, right? So this is more modern stuff, 1000 watts, right? Why not? And of course, if one of those cards is not enough, then you can bundle them. In this case, you can buy one box that contains 8 of those. It's, of course, quite expensive. You can see that it is 6 huge cases, and I think it's only one half of it. I have never seen it, to be honest, in a server room. And just one is 5 times the typical rack consumption. So if you imagine, having just the power consumption, the cabling for this, it's something very different to what we are used in our traditional server rooms. Of course, the heating is a problem. Again, very different to what we have with the traditional servers. But you can maybe do the training on one of these and not on your servers, right? So there is also a CNCF effort that is called environmental sustainability, and this is something that would like to further introduce some concepts that we should go greener. There is also some term comes there that is called green ops, because there are not that many ops terms, you know. So if you would like also to measure these consumptions, you can check out the talk over there. But the basic idea is that instead of counting CPUs, token these days, etc., you can also factor in the power consumption, and you can have it as some key decision, not just like how much are you going to consume, but for example, if your data center will allow to consume more in the future, if there is still some gap for you in that country, region, etc. They have some meetings, so if you're interested, definitely join them. I think that except for Project Kepler, they have still several other interesting trades and topics that are appealing. And now finally, we have a demonstration, right?
Right. So we prepared a small demonstration, and of course, if you want to go green, you buy something like solar panels or windmill, and if the sun is shining, the solar panel is producing the electrical energy, and everything can be running. But if there is winter, the weather is cloudy, the solar panels do not produce enough energy, so we have to take the energy from the power plants, from the coal power plants or other kind of power plants, which is not so green. And you don't want to take too much energy from the power plants, and so you want to scale the devices or the nodes or the servers that are not necessary for the regular traffic. So to demonstrate it, I will explain what is the setup. Here we have the solar panel, which is connected to the USB tester via the USB tester to the power bank. The USB tester is giving us the number of watts or the energy that the solar panel is producing. Unfortunately, we do not see the sun right here, so we brought a halogen lamp, which is producing the light for us. Then we have two objects, or the two devices, the fan and the LED light that presents the devices that we want to scale if there is cloudy or sunny. If you imagine in the server room, we need to cool the servers. So the fan is our priority, and we don't need to light it or have the light there. We could have the flashlight or something like that. So we will scale down the lights. So as David said, on the main laptop we have the HQ cluster, which is connected to the Raspberry Pi, and the Raspberry Pi is controlling the devices. Have I forgot something to say about it?
No, let's go on.
Okay, so now I will show you, because now the solar panel is not, the light doesn't shine on the solar panel, so only the fan is running.
Maybe can you switch to the dashboard?
Yes.
And I will be your assistant, if I may, right?
Okay.
So we have nice dashboard, right? And the dashboard actually showcases what amount of watts of power are we going to get from this thing. So, I would just casually have it over here, and if everything, our effort for last several months will work, we should see some spike over there. By the way, it is getting kind of hot over here next to the lamp.
the pod is started, but we don't know. We do not see it in the Grafana, but we see that the LED started or started shining. Maybe there is some problem. Okay, we have the metrics in the Grafana right now.
So that's it, right? No, I'm kidding a bit. So what we basically wanted to showcase is that you can definitely scale like based on the, in our example, sun. The reason why we have the halogen light is that we also wanted to go much greener than this with something like a headlamp, but it has a different, what is it, frequency of light?
Yes.
I'm not sure if the frequency is correct word, sorry. But so it is not able to trigger the solar panel at all. So this is why we have the lamp. But so several trivia questions, because as I mentioned in the previous table, people typically don't understand the consumption much, right? So if I would ask you, what do you think is the power consumption of this fan? What do you think? 3? Some other number? 5? Okay. It's just a half of a watt. Petr is much greener. I wanted to have much bigger thing, but this is the green one. Okay, how about these? What do you think? This should be between, I think, 1 to 5, something in between. Probably also depending on the light, right? On the color of the light that they have, right? And what about this small one? 500. Up to 500, I think, because I cannot even look at the thing, probably it's like 500. So we just want to showcase, that the devices, even though, they might look similar in size and shapes, it's kind of sometimes hard to estimate, and you really should take care of the number that is, below somewhere on the tag when you buy them, because you can still save significantly just selecting some other products or maybe having something smaller. So we apologize that we are not able to blow, up to the last corridors, but still, this is the green thing.
Okay, so if you want to see the scaling, right? We show the
yeah, we can
scaling.
go on a scaling.
So you might have seen that we have the output of the USB tester, but we want to also show you the scaling in the real time. So now only the pod for a fan is running, and if the David puts their solar panel, the metric gets to the Raspberry Pi, where Prometheus scrapes the endpoint or the metrics. And based on the metrics, the KEDA, the HPA scaler, scales the pod to the 1 replicas, which gives the request to the Raspberry Pi to start the LED lights. So now you can see that the pod is running, as well as the LED device. And if we take out the solar panel, it's soon start to scale down again.
Okay, can we maybe showcase also Argo CD and how does the remote cluster thing look like?
It takes some time, so yeah, it started now, and the LED is turned off.
Okay, so I just wanted to showcase how does Argo CD work with this remote. So again, we are running Argo CD on the cluster over here. We have a second cluster on the Raspberry Pi, and if you look over here, we have factory Pi. Everything with this prefix is being run. You can see or tell it with the destination. So the destination, in fact, if you would go over here, it's other cluster that is remote. So the thing is that you would get a very, let's say, typical feeling, and from this Argo CD you cannot even recognize that something is running afar, and you have, as an administrator, a very good, let's say, experience. Can we please also show the Kepler dashboard, just to showcase it? So Project Kepler, as we have discussed, you can imagine it basically as something similar to node exporter. So it needs to run on the machine, it is measuring. It uses the eBPF, if I may, highlight it again. And these are the results that you can have from it. So there are multiple details depending on like which zone would you like to have. You can, but bear in mind that it basically is like self-sustained on a single device, and it tries to divide to ratios the power on that particular device. So basically, like having any other segmentation is, let's say, I would say questionable. This is probably one thing that is interesting. So total power consumption, and you have it for you can have it for a namespace if you like. There are much more detailed like explanations of these basically calculations, because of course you can switch some. Maybe let me start from other part. It is assuming that you are using Kubernetes in some like typical way. So for example, in a kube system, everything is like idle bundled in, and it should not be calculated differently than by ratios to other namespaces. So there are some knobs that you can maybe turn, but it's they are probably not that important.
So probably that's all for the demo. And let's get back to the presentation. Můžu? Další? Okay.
So what are some takeaways? First of all, as you have seen, being on edge is like absolutely mature. Even with the regular tooling we have, you don't need to like install anything special, work with it any special. We are using regular Argo distribution. K0 is again, very, very standard-like, I would say. The power consumption is now observable as you have the number of CPUs, memory, etc. So it's especially easy to have yet an additional dimension of your metrics, if you like. And of course, given what might await us, that we will need more power for the AI we are using, on our laptops, we probably should also think about this one. So if you are now working with cloud, what do you think is the best decision, or like, how can you help with this problem the best? Meaning, what you should do in the cloud to improve your carbon footprint? Should you go with smaller VMs? What do you think? Does it make sense? Maybe, right? If we can please have a next slide. Like, surprisingly, this is a comparison of running the same VM through the Google Cloud in multiple regions. So actually, what you can do to help is not like first thing to run smaller, this is by default, right? But to relocate to the locations that have a better ratio on the grid. So basically, if in Paris, they are able to produce more effectively with less CO2 emissions, this is the data center that you can use. And as you can see, some of those decisions are like 2 times, for example, for Europe West versus Europe West 9. So I think that a lot of us can like decide in which region to run their services. And this is yet another thing that you might consider next to the networking latency, etc. Because if you are producing just half of the CO2, well, it might make sense. If you would like to hit the planet hard, let's go to Mumbai probably. So we definitely encourage like some call to action, not just like to sit here and watch, So please try it. The thing how to do it, probably the easiest way is that you go to your cloud, and there are already dashboards in all of those major cloud providers, and you can check, how much are you consuming. They are factoring, of course, much more than the CPUs or just the VMs. Also from their other services, they do have some like ratio or estimations, and I think that you would be very surprised, how much you typically consume, or even like how much you help. So in my mind, at least, this is also about like being aware of the problem. Because sometimes like making the decisions that help significantly, as you've seen, 50% cut, is maybe just a different data center when we don't care. Also, one thing, except having smaller VMs, is switching to Graviton, which means ARM architecture. these are more efficient. There is a case study, if you like, to see on some like bigger scale that did happen. So that's all we had. Thank you very much.
Thank you. So I'll probably take the first one. Okay, so how much green computing do you do at home or at work? Okay, honestly, I don't know because we don't measure the emissions or the sustainability of the clusters. So the presentation was the first idea to start doing it.
If I may like input my take on this one, you know, previously, like a few months ago, I was working with my laptop, so I could like factor the decisions on my servers or like on my laptop. But now, you know, when I'm using AI models a lot, I think that I got like significantly worse, like 10 times worse than it was like just a few months before, unfortunately. No, but otherwise, really, if you will look even at that grid ratios, this is some first thing that you can work. We've been multiple times in a situation when we could factor this in the past, and probably we will in the future, I believe.
Okay, so the second question, yeah, the halogen lamp. I've tried. The initial idea was to trigger the solar panel by the LED lights, and it didn't work at all. So I put it to the regular sun, and of course, it worked. But then I asked why I was wondering why it doesn't work on the LED lights, and as I was advised, the LED lights have the different light frequency, which is solar panels are not used to. So the closest frequency should be the halogen lamp, and it worked. So that's the reason why we have halogen.
But we are not experts, you know, in the light spectrums. But I think that we are expert that if you have a lamp that has 500 volts and you are able to produce 1.5 on the solar panel, it's a green solution, right?
Very green, yeah. Okay, I can answer.
To be honest, up to my knowledge, I don't know. I don't know. I mean, I am not aware of any other cloud provider that would have like. What do I mean by it? If you, for example, choose ARM devices, you typically get lower price because they are cheaper to run. Typically, by the power, but also they are probably cheaper to buy. So I'm not sure if I have seen some like different, for example, different prices. You can definitely bet that, for example, in AWS, given that each region has a different prices, this is factored in as one of the inputs. But also, you know, carbon emissions do not exactly reflect to the price, because if you would compare the price of 1 kilowatt in India and the CO2 emissions in comparison to France, I don't think that these are like much related. So maybe Europe is, you know, on the frontier of it to have some connection between these two. But I think that unless there will be some connection, that if you are just polluting, you need to pay more in some like transparent manner, probably this is not going to happen, that we would be able to get some services that are greener, maybe even cheaper. Like, I don't think that there is a connection so far. Okay, so that's all. Thank you very much.
Thank you.
Our next speaker is Liene Luksika. She will bring a guided tour through our digital sovereign ecosystem, and I will pass the word to you.
Thank you. Now, according to the previous talk, I need to re-evaluate or at least check the carbon footprint of our cloud service providers because we tend to use smaller ones, so now I'm very worried of their input, but let's see. And actually, this is one of the only few countries where I can leave special characters in my last name, and I'm sure you can pronounce it. I'm a product owner from a company called Vision in Switzerland. Vision is spelled as VSHN, but it's intended to be pronounced as what your eyes do. And we're a rather small DevOps company. We take care of the processes around software development so that the developers can focus on writing code. And we work with any on-prem, private, public cloud infrastructure, and we use Kubernetes as the basis for managing and orchestrating configuration, backups, monitoring, everything around your infrastructure. It has been mentioned already a couple of times that waking up at 3 a.m. is not fun, and we have hacked our way around that by having offices in Zurich, Switzerland, and also Vancouver, Canada. Of course, we offer the possibility of a sleepy on-call engineer from within Switzerland if that's the absolute requirement of our customers. But you know, nobody wants that. We have a company policy that we do open source first, and we are also very proud to have a few of our own open source tools. One of them is KTAP. It's a backup solution. It's also a CNCF incubating project. Does anybody know Velero? Yeah, so KTAP is the other one. And that's ours. And we are very proud of it. We also have Project SYN, and that one is a pre-integrated tooling system for updating backups and alert management for Kubernetes applications. It works mainly with OpenShift because we use a lot of OpenShift. We also have Espejote, which is a very, very new one. And that's intended for heavy lifting for the OpenShift customization. And it works also very well with Project SYN. We are also very friendly because sometimes you need tools that are not open source. So we partner up with a lot of different companies, including, as already mentioned, Red Hat OpenShift, because it's just, you need some solid infrastructure to run your services on. And actually being here, for me, feels a bit like homecoming because my husband is Czech, and he's actually from Prague. And this gives me a chance to visit my family. And I don't know about your families, but for me, when visiting them, they make me eat. they make me eat a lot. And that's why, for me, I will take you on a food tour. And as everything in Czech begins with chlebičky, including this conference, our digital sovereignty journey also begins with chlebičky. And it all started for us with a very nice customer project in a controlled environment where we were allowed to build something cool that sparked interest for us. It started with one cloud, one control plane on the same cluster. You get standard t-shirt-sized instances from only 2 databases, and we managed to provide it on Kubernetes, leveraging the Open Service Broker API. And we used it as a patch and transform, basically. The customer comes to Cloud Foundry and orders either a MariaDB or a Redis instance in a specific size, and that request then gets passed to Open Service Broker API that translates it to cross-plane language. Then cross-plane does its magic and spits out an instance that the customer can use. It had some features like alerting. Of course, everybody needs alerting, and that one was done by Prometheus and Alert Manager, and then passed to OpsGenie backups, our user responsibility. Then all databases were standardized, and also updates were performed in a manual manner on scheduled time scale. It was basically like going to a typical Czech diner or KCD lunch. During lunchtime, you get 4 options, and it works. It just works, you know. Everyone's happy. We're moving on. And I need to remind that, or actually mention that this was done back in 2021 when Crossplane was version 0.17. And from there on, our journey began, and we got inspired to create other different products based on that. And I'll get to it step by step, but I mean, you've already noticed that I've mentioned a tool named Crossplane already a couple of times. And it's important for the context, because for us, this tool means a lot of different things. It has brought a lot of joy and also pain and some dark hairs, or not so dark hairs anymore, in some engineers' heads. Actually, at this year's KubeCon, Jared Watts, who is one of the masterminds behind Crossplane, said that Vision has been such an early adopter of Crossplane when it was bleeding edge technology that we got some deep cuts, which is true. It really is true. And for the people who are not the 2 engineers from Upbound, I will remind that Crossplane is a very powerful control plane tool. Crossplane lets you build your own control planes and manage cloud-native software. It works as an API. It brings up abstraction levels, and the control planes exposes the API so that you can use it to configure any cloud-native software. When an object drifts from the desired state, Crossplane tries to fix it, which also can cause some issues sometimes. But that's a different story. And yeah, the most important part is that it works with cloud-native software, which is why we used it, which is why we needed to use it, why we wanted to use it. Also, back in the day when it was very fragile. We actually started also a Crossplane competency center in Switzerland. Because we have had so much experience with it, we wanted to share it with others and maybe help them have a pat on the shoulder when it's needed, or a little rubber duck, because sometimes that's what you need. And well, now that the chlebičky are gone, moving into main, as in today's main, webshop-Knedlzelo, we call it AppCat, or Application Catalog. It's basically an app store for engineers, or a marketplace of managed services that offer some standard services like Postgres, Redis, identity management like Keycloak. Also, OpenBOW is coming soon. And we built it very similar to the customer project. We called it Framework 1.0. It's a framework of automated service provisioning and day 2 operations. We got inspired from the customer project, so we decided to build it very similar, but it should be bigger and better. It should work with every cloud service provider, big or small, it doesn't matter. We also thought that we will rent applications, rent the managed services from other cloud service providers, because, I mean, who doesn't want 7 types of Postgres, right? The choice is important. So the service definition XRDs will define the API for the end user. Then compositions define what happens when the service is provisioned. It instructs how the Helm should be deployed and created. Then Crossplane does the magic again in the background with the compositions, and it uses Helm. But you know how it is when you want something very simple and easy, because customers have requests. So their requests started coming in as feature requests, and they really made sense because, I mean, backups are nice, self-service restore is sometimes very much needed, logs, everyone needs solid logs because you need to know what's happening. metrics. You need to see those beautiful Grafana dashboards, and you want to have on-call or not so on-call, but just proactive alerts of what's happening. Maintenance needs to be self-service. You want to schedule your own maintenance windows. It has to be automated. Version upgrades, major version upgrades, scaling, because high availability, not high availability, that is important, right? We need that. And some very specific feature requests started coming in, which is fine. We can cope with that. And this all led us to build on top of the initial framework, which led to some issues. And if you have tried making Knedliki on your own, you know what I mean with issues. Because even if you just change one parameter from the grandma's recipe, it can end up uneatable. No one wants that, right? So we fixed the framework. We thought, okay, let's just not use the provider applications because it's just not needed. Provider for cloud service we'll use just to provision buckets. That kind of works, that's fine. Then provider Helm is good, we can work with that, let's keep it. Then we decided to not rent out services from other cloud service providers because they constantly update something and it's too much effort to take care of our infra, their infra, integrate everything at once. It just, no, it's too much. And nobody wants 7 versions of Postgres, apparently. So we cleaned it up, but we wanted to make it better because it's needed. And well, actually in the customer project, there was split architecture. Split architecture as in there's control cluster and the service cluster. And by introducing split architecture, the logic should happen in the control cluster and all the services live on the service cluster. It worked on the customer project. It should work also in our use case. But this is like when you and grandma are in the kitchen. You know nothing about cooking. Grandma knows everything. But you're the one who's cooking and grandma's giving instructions until grandma leaves. And you know nothing what's happening. Suddenly everything is burning, it starts smelling, you scream, you cry, nothing happens. By the time grandma again enters the room, it's just, no, it just doesn't, no, it just doesn't work. So introducing split control plane for us made the communication just impossible. The reconciliation loops were not happening, and Crossplane doesn't support natively different cluster communication. Provider Kubernetes does, but you don't want to do that because the complexity is just too much. And the added benefit is very, very doubtful. So again, we cleaned up our infrastructure and we thought that, fine, we are going to go with one cluster only. Everything lives on the same cluster. Everybody talks to each other. It works. And we are reworking this architecture so many times, and it's just constant trial and error, trial and error, and we all are just getting hungry and very frustrated. And when we were looking at what's happening for us, AppCat started to look a bit like Gaudi's Sagrada Familia. It is something, it's intended as something very magnificent and big and beautiful, and it operates even though it's under construction, but for now, it remains just an enormous construction site. And it's demotivating is the word that the engineers used. So we went back to the drawing board. We went to a greenfield approach. And for inspiration, we went to the CNCF landscape. Are you familiar with that? Right. This is actually pre-filtered. I'm not showing you everything, just for the sake of actual representation. So here you see only the CNCF and open source projects. And we want to stay true to our company philosophy, which is open source first. And we actually had a moment, few days in the Greenfield workshop, where the other group just burst into the room and was like, we are trying to reinvent Crossplane. Let's just go with Crossplane the proper way this time. Because we have been using it for so long, it got so tangled and messed up with a lot of patches and a lot of different things on top of that, that it it wasn't maintainable anymore. That's why we were reinventing the wheel, so to say, but this time in a clean way. And to be honest, now there is a standardized, somewhat standardized way, somewhat genuine approach how to do that. And we also decided to clean up the day 2 operations. So the framework 2.0 for us is a proper cross-plane V2 implementation, using it the way that it's intended. And well, Yuri before today asked me if we use the guidance from Upbound of how to write compositions with Go, and no, we don't. I checked with engineers because it wasn't there when we started. But we will. Now we will. And with Framework 2.0, we want to really leverage the cross-plane 2 functionality and work the intended way. The working title of this framework is Apps Lab. We are still thinking if this sticks or not, otherwise we go with AppCat. And we will use composition functions wherever possible. We just want to stick with that. And the logic should be in the composition. And only if absolutely necessary, we intend to write our own functions. We currently have the logic in the functions, and it's just enormous, gigantic function. And instead of passing the logic to the function, we pass parameters, which works, but it's not really sustainable, and it's prone to error. And it can fail. Like I said, we want to clean up the day 2 operations, because currently it's a big mess, and it's sometimes very nested, and it can cause problems. The engineer actually the other day said that building something complicated is easy, but building something easy is really hard. And we are trying to really decouple this. We want to take care of the logic side. We like crossplane and we want to use it, but we want to move it away from the service maintainers, that they don't have to use it because it's our choice and we want to. Actually, now that we're done with main, it's time for a second main because we're in Czech. And you haven't really been in Czech Republic if you haven't tried Svíčková. You might still have some chance, so, you can still do that. And the main, in this case, is a Soeren app store. We call it Servala, and it's intended as a connection point for businesses and developers and cloud service providers to offer a scalable and easy-to-use cloud-native marketplace. And Soeren has been used, I feel like, in every second talk here. And in this case, Soeren means without a vendor lock-in, independent. And it looks like this. It's actually also a split architecture, but split architecture not for AppCat use case, split architecture for the user, because AppCat, so the service catalog, lives on the worker cluster, and the logic with which the user communicates lives on the web portal, which is like a management cluster. Everything is separated. We actually intend to work with different cloud service providers, but in a clean way, in a clean, separated way. We have a bit of time for bingo, so anyone uses 4 of the tools listed here? 1. Is there a 5? Wow. Okay, good. Well, the first one that we use is KTOP. Remember the backup solution? We use it for backups and restore. Victoria metrics and logs, because it's very nice and user-friendly. We like Victoria. Grafana, because there is just nothing better at this point than Grafana visualizations. Everyone's just so used to them, and they're hard to not like, right? The green is appealing. Alert Manager for managing alerts. Renovate for staying up to date, because no one wants to do that manually. Project Syn, as mentioned before, Project Syn is for the configuration management. Then Talos. Initially, we worked heavily with OpenShift, and for this specific use case, we went with Talos because it has a smaller footprint. It's more raw so to say. And we actually use Talos together with Toth. Toth is a small open source tool, open sourced by PostFinance in Switzerland. Hello, PostFinance. It's a very nice tool, and it manages machine configs and bootstrapping, and we like it. It's a very, very clean, very nice little tool. We also use Espejote, which is our internal open source tool. Then, yeah, what didn't I mention? Everything else, Argo CD, of course. Everyone uses Argo. We also have very strict requirements for infrastructure for our cloud service providers. And that we learned also the hard way, because you need to have a stable infra to be able to provide a stable product for the customers. And for us, it's important that the API to manage the cloud resources is there, is maintained, and we can reach out to the cloud service provider if we need something more. The self-service VM provisioning is available, custom VMs that are image-based, then object storage that is S3 compatible, because everybody needs storage, fast SSD block storage. We need at least 100 plus storage device attachments to the VMs, then managed load balancer with at least 100 listeners, and we had to request to increase the listeners because it also just didn't work well, a good firewall. And actually, you know what's for dessert? A ecosystem in the shape of babovka. Because no one can do it alone. You need to have a circle of trust to move forward with this. And for us, the circle of trust looks like a cloud service provider with a stable, trustworthy infra, a software vendor that creates the applications and keeps them up to date and not just lets it live out there unmaintained, an implementation partner who can package the application so that the customer can just use it. And of course, we also need managed service providers who are ready to take the spatula and wake up at night and make something cooked when it's still a bit raw and shaky. And that's how our ecosystem looks like. Thank you. Good.
Thank you. Thank you so much. And we will have a break, a 15-minute break. So grab your coffee, refreshment, a walk, whatever, or stay here. And we will see next presentation in a while. Thank you once more again. Hi. I like to introduce Filip Sedlak, his presentation, watching TV, so you don't have to. I'm so curious about, because I like to watching a TV as my rest time, during my rest time. So I'm so curious why I can't, or
well,
you do
you can.
instead of me. Okay, thank you. So stage is yours.
Thank you. Yeah, actually, it will not be only about TV, but radio too. So, I don't know, can we start? Yeah. Oh, so it's there. Oh, sorry. Yeah. First, a quick intro about me. I'm more of a generalist. I studied chemistry. I co-founded a machine learning startup, and I worked at Google, at Twisto, and now I'm helping startups scale up a bit. So at this moment, I work for Media Board. That's a media monitoring company originated here in Prague, and we do monitoring of basically all the media that you can imagine. We are scraping the internet for online news. We are reading print news and magazines. We are looking at social networks. And what this talk will be about is television and radio. So that whenever someone talks about a topic that is interesting to you, about some brand or some industry you work in, then we can notify you, provide analytics, and so on. So that's a tool for PR people. So you're not the target group. But what's interesting with us is that we are dealing with a fairly large amount of data, and we have a fairly big live index, including archived media. So today, I would like to do a user talk about Kubernetes or cloud-native technologies. So how are we using that for this big data processing, where it works well, but where it falls short for us? Because we are quite cost-sensitive. We are still a small company. We are now in several countries like Czechia, Poland, Slovakia, Slovenia, Croatia. And we are trying to open 1 or 2 countries per year. So we have to look at our costs. So, for example, running everything in AWS is not an option for us because it would be just too expensive. What we are facing quite often is that there are slight incompatibilities between the providers of Kubernetes at OVH is different from Kubernetes at Amazon, different if you rent yourself, and so this is how we are dealing with that stuff. And I saw a lot of talks doing LLMs or AI, how everyone is using it. I'm trying to refrain from that in this talk. So we have been capturing the TV and radio for a long time, basically almost from the beginning. But it was always a second-class citizen because the online and print was the main focus, and now as the product is more polished and we are trying to target more and more customers, it's more important, and especially when we are opening new countries. So we thought we already knew how to deal with this data, and we just needed to make it a little bit bigger. So with that in mind, we said, okay, this will be a short project for, I don't know, 2-3 months, and we will just rewrite it, and we are good. We know what we are doing. 1 year later, I'm doing this talk, and we are still not finished with setting up the system as a whole. So this is the story about what can go wrong. So at this moment, we are monitoring about 350 channels, and this this is expected to grow at least a double, which is different than our situation in online monitoring, where we currently capture about 5 million articles per day, and we know we don't have to scale much more in that area because there are just not that many articles written globally. We need to be more precise in that area, but we don't need to scale up. So here in TV and radio, we deal with larger amounts of data, and we are growing quite fast. So the workflow that we do is that we need to watch the station, the TV or radio station. We just record the stream of the data. Then we need to get the program. Like we need to know that, okay, today there is news at 7, but during weekend it shifts to 8 p.m., something like that. And we match which of these programs are interesting to us. We have to transcribe it to text. We automatically clip it to stories. So for example, if you have news at 7 at Česká televize, it's composed of many stories, and each one is an independent article in our system. And sometimes there's a human in the loop who has to verify that this is correctly done, that it starts at the right time, that the people who are mentioned there are those people, and so on. So basically, this is what we need to do. And now, how do we do it? So I don't know. Does anyone of you have worked with media data? Like how many people? Okay, not that many. I didn't have much experience with this either before. So if you are looking at I don't know, there is a web page, Radio Garden. I don't know if you know that. You can basically select any station on globe and just listen to, I don't know, some Italian radio or Arabic radio and so on. So they stream data to us, but how does it look technically? In the radio example, that's like an endless MP3 file that you can just connect with your browser to, and it just plays, and you download it in real time, and you get an endless stream of bytes. But this is quite unwieldy to store. You cannot store an infinite file in your system. How would it work? So in order to deal with that, there are some streaming formats that deal with this problem. That there is HLS, which is from Apple, and it's the simpler one. You have a playlist of segments. So, for example, here in this example, they cut it to roughly 9 seconds. And each of these segments is an independent media file that you can play, and the client just refreshes this playlist, and you store those media files in CDN somewhere, and that's your streaming. There's a competing format, MPEG-. It's ISO standard, much more complicated, but yeah, it works basically the same. You also chunk it to some periods of time, and you deal with small files that you have to then stitch together if you want to play them. So what we had in mind at the beginning was that there's this stream. We have a recording box that cuts the stream into chunks. Stores some metadata into SQL database, and then the main system wants a clip for a specific time, and this recording system can give it to the main one. There are a few issues with that. One thing is that when you are scaling up this thing, you want to parallelize it ideally per channel because they are independent, and not to have everything in a single monolith. That was easy to start with. It was easy to develop, but we had to then carve out some responsibilities to external systems. One thing you have to deal with is the uptime. If you are crawling online articles and you are down for 5 minutes, nothing happens basically. If you are down for 5 minutes when you are listening to radio or watching TV, the data is gone. You have to then fetch it somewhere from the archive after it is available. It's a pain. So there are real uptime requirements for this kind of service, and you want to contain problems to single channel ideally. The other thing is the storage. You don't want to rely on local storage again because of losing the storage means that you just don't have the data, and you also are tied to specific box. The problem is that there's quite a lot of files. If you have just 100 channels and keep them for 2 weeks, it's 12 million files, and that means if you have 100 channels, that's 10 uploads per second. So now we are doing about 40 uploads per second, and to our surprise, this was already enough to break, for example, Hetzner object storage, and I don't know if it was related to our issues, but sometime during the beginning of this year, a part of the documentation in Hetzner started to say that, oh yeah, this service is good mostly for archiving and not frequently access data. Us rewriting 12 million files every 2 weeks or even more, it was not a good use case for that. So at the beginning we thought, oh yeah, so let's use object storage. There's many providers of this kind of service, compatible API, but they are not all made equal. Now we are using Backblaze. It's workable. It's not as good as Amazon, but for a fraction of the price. So we are using that for now. And we split the system into multiple stages. Most of them are modeled as Kubernetes deployments running in parallel, maybe in several replicas. And at the beginning, there's the recorder box that has its own storage. It caches about 1 hour of stream, because the problem in the beginning was that we were depending on a central database to store the metadata. So now we split that up, and even if our database is down for a short while, we still have 1 hour to catch up with the recorded media. So that gives us some leeway, and it's a balance that there is a very simple recording box. We have different provider formats that are implemented there. It normalizes the data, but doesn't do much more. So it's also something that's quite easy to do with Kubernetes. The problem is that those things now need to communicate with each other, and I'll get to that a bit later, what are the issues with communication with different Kubernetes clusters. So there's a slight aside that we didn't have that much experience with media formats, and there was one issue that bothered us for quite a long time, that because there are different streams in the in the media file. There, you can have video and audio if you are watching TV, and we had problems synchronizing that. If you then assembled those small chunks, the audio and the text was slightly off compared to the video, and we couldn't figure out why was that before we really understood how the media format works, and the synchronization was getting more and more wrong the longer video you had. So the issue, if someone is dealing with that, was that when you cut to 10-second files, they are expected to be not independent. They are dependent on each other because the sound and the picture can not be can not end and start at the exact point in time, and this is expected because if you then stitch this together and you say that okay, here I remove the gap here and I remove the gap here, then everything works perfectly. But if you reset the timestamps like we inadvertently did, and just put the files together like independent video files, then one stream might get those gaps, while the other one might stitch perfectly together, which gets you a very short delay every 10 seconds, and then after several minutes, it's visibly off. So if you're working with media files, there are several different layers of timestamps. You have a timestamp that tells you when a particular frame should be shown up, when it should be decoded. So yeah, something that I didn't think I might need to know. Now we are dealing also with multi-cloud and multi-region. We didn't want actually multi-cloud, but we were a bit forced to, because the providers of the signal, they sometimes require that we consume the signal in a specific country. So, for example, if you are recording Croatian TV, you have a contract that says, "Oh yeah, but we deliver only to Croatia," because that's what their copyright allows them to do. So we need to be present at several regions, several countries, and again, we cannot do it really with just AWS or Google Cloud, because just transferring all the data across those clouds would be too expensive. So we are somewhere we have our own hosted Kubernetes. Somewhere we use, for example, OVH. And the thing is that each provider gives you a slightly different way of doing things, which is sometimes a bit problematic. For example, setting up firewalls and so on. Storage. This is the other thing that doesn't match perfectly everywhere. One thing I wanted to mention here is that in this system we do stateful rollouts, so like stopping background workers, do changes in the database, update web workers, start the background workers anew. This is something I see a lot of people are moving to GitOps, but not many people are talking about how they are dealing with this kind of problem. So that, yeah, you want to have a source of truth in your Git, but how to get there might be a stateful process. So I would be really interested after a talk to talk to any of you who are dealing with this issue, and how are you solving that? Because we don't want every of our versions of code be fully backwards compatible with anything that might be running in production. So we try to minimize the time when it might cause issues, and we are trying to just make it easy to deploy new things to database, because our database changes almost daily. And if we did stateless rollouts, just deploy anything that is the new version, that would mean slower development, because you would need to phase out the change of the database in a different change set than change of the code that depends on it. So yeah, if anyone has experience with this, I'm interested to talk to you. So here I actually like working with Kubernetes for this use case, because even if it's not 100% equal, still it gives us cross-cloud portability. And because we have quite a bit of channels, and each of them has its own deployment and ingress and so on, we really like the programmability that this does. So our application acts as a Kubernetes operator, and based on our database state, it starts or stops the Kubernetes deployments. So yeah, this is the story how we are using Kubernetes for watching a lot of channels and scaling up. We thought it would be an easier problem. We didn't know about the issues that we would encounter, for example, with the legal stuff around copyrights. We didn't know about the slight inconsistencies between different providers. But if anyone has any question, I'm here to answer. Thank you for your attention.
There are no questions. Definitely ask me. Maybe I will help you a little bit with the problem.
Okay.
Maybe another way. Maybe we found 2 or 3 solutions. You'll be fine for a discussion. And thank you for your time and share your project.
Thank you. So if no one has questions, I have questions for you. One is the one that I already asked about the deployment story. So currently we are doing a Python script that generates the manifests and does this stage rollout. But our infra people don't like that, because it's not like standard tooling. And the second question, what is your experience with multi-cloud, and how do you deal with networking? Are you using public internet or VPNs to connect between clouds, and just how you do it? So if anyone wants to share with me, just please find me out. Thank you.
There will be one more presentation in front of us, and then a raffle. So stay tuned, take a coffee break, walk, whatever, and see you on the next one, the last one. So this is our last but not least time. I would like to introduce Jussi and Soeren with their presentation, Breaking Free of a Single Data Center. So I am curious, how many data centers will be then when single is not enough? Good? Stage is yours.
Let's see. Let's see.
More is always better.
Yes, absolutely, yes. All right, hey, good afternoon, everyone. Thanks for sticking out here this long to join us. Today we're going to talk about a bit on the kind of architectural patterns, how you can stop thinking about clusters and as being placed in single data centers, and really embrace geographically distributed AI platforms. And of course, every tool that we're going to be mentioning, everything is of course open source, so no vendor lock-ins there. So I'm Jussi. I'm working at Mirantis as senior principal engineer, whatever that means. I've been working in the community or within kind of the community for past 10 or so years already. So I guess you could call me also hard-headed because I'm still here doing Kubernetes and other cloud-native stuff.
Yeah, my name is Soeren. I'm working at Logsight AI, and my origin story in the cloud-native field started out with OpenStack, and then some time I switched over to containers, and nowadays I'm building infrastructure for Geo-Distributed AI training.
All right. Quite often when we think about platforms, and especially kind of AI platforms, we think about things as really being single data center. Everything is more or less homogeneous in a way. You have same operational model for everything and so on. The reality is unfortunately quite different. One of the main drivers for that is the scarcity of GPU resources. I guess you've all seen it. Even the major cloud providers actually run out of capacity every now and then. Or at least for us, who are not in the billions of dollars of revenue, we are probably the least favorable for them to actually get our hands on those resources. Or if you're lucky enough and you actually have some resources available on your own on-premise environments, those might be scattered around different data centers, edge locations, research labs, and so on. To make things even worse, you probably will run into different generations of hardware, different vendors, of course, different VRAM sizes, different driver versions, and everything. Now, we all know that here in Europe, we're kind of driving towards being sovereign, right? Which is a super good thing. But it doesn't, unfortunately, help things, because when you develop your applications, you increasingly get requirements to place different kinds of workloads in certain environments or geographical locations. So it really drives the landscape of the infrastructure to be super, super fragmented. So,
My bad, sorry.
So why is this a Kubernetes problem? Well, why do we want to have Kubernetes in the picture in the first place? Well, we're at KCD event, so we all love Kubernetes so much that we want to put it anywhere and everywhere, right? More seriously, I think we as an ecosystem are kind of standardizing on top of Kubernetes. So I think it's more or less nowadays like every single week there's some new AI-related tool popping up that builds on top of Kubernetes and the patterns of Kubernetes, being declarative and everything. But since the fragmentation, now the workloads are actually spanning between geographical locations, spanning clusters, sites, regions. So you really have to stop kind of thinking about single cluster as your target for the workloads. It also means that you have to start thinking of managing multiple clusters. You probably are already, but increasingly the number of clusters is growing. So your multi-cluster orchestration really becomes your foundation of running AI wherever you can get your hands on GPUs. Whether you can actually order them and maybe get them like 6 months later if you're lucky, or if you can find them from your cloud provider or data center provider.
All right, yeah. So for us, this whole setup of these fragmented resources that are located across different research clusters, on-premise environment and edge environments, basically became very concrete through our collaboration with Sprint, which is the German federal agency for breakthrough innovation. Basically, they are partly inspired by the US ARPA model, and they run challenge-style innovation programs for topics in which they see the potential for disruptive progress. And one of those programs is this Composite Learning Challenge that we are a part of. And composite learning, in case you haven't heard about it yet, which I also hadn't before we started this project, is basically about combining distributed, decentralized, and federated learning mechanisms. So basically, Sprint here is looking to train, or for approaches to train AI models across heterogeneous and distributed systems, without assuming one centralized data center where all the compute and data is co-located. So they are exactly targeting such an infrastructure that Jussi was talking about in the beginning. So when we started with this project, we wanted to approach this challenge from a systems and infrastructure perspective, because this is not only a machine learning problem, but also about how to make these fragmented GPU resources operationally usable. So this is why we started this project, and basically our goal here is to build an open and Kubernetes native operational model, or a platform if you want to call it like that, for geo-distributed AI training. And once we framed it this way, the platform requirements became quite clear to us. For instance, this platform has to be provider agnostic, since we cannot assume that all GPU capacity comes from one cloud, one provider, or one data center. Also, we need to support heterogeneous hardware, since such a GPU fleet is typically also not a uniform set of identical machines, right? So therefore, we have to deal with different CPU architectures, GPU architectures, as well as vendors and types, and their respective software stacks. For instance, CUDA for NVIDIA or ROCm for AMD. So therefore, this hardware diversity must become a managed platform concern, not a manual per site work. And finally, in this process, we decided early on that we wanted this platform to be Kubernetes native, because we want to build up on these Kubernetes APIs and use and build upon the cloud-native ecosystem that is already out there, instead of reinventing the wheel and building our own separate infrastructure control plane here. So after we have thought about these requirements, right, we started out and looked around to find out what is already out there and what Kubernetes native building blocks we could maybe build upon. And that is how we found these Cosmos open source ecosystem that Jussi is going to talk a little bit about now.
Yep. So how do we get from this fragmentation to really get like a unified platform that we can actually treat as a single platform? If we think about the foundational level, kind of the sort of the infrastructure level of things, each of the environments have different operational constraints. In one data center, you might have some operating system images available, some other site cloud provider has some others available, or at least different versions. And it basically means that every single environment you deploy to, it is actually different. How much different, that's a different discussion, of course. So for the foundational level, we want to have Kubernetes as boring as possible. That's where the K0's CNCF Sandbox project kind of comes in. It provides us, well, the Kubernetes, of course, but it's really built as a kind of a minimal possible Kubernetes package in a way. So K0 distills the whole of Kubernetes into one single binary file, which has virtually zero dependencies. Everything is actually statically compiled, so I can drop the exact same binary on Ubuntu, Red Hat, Alpine Linux, whatever. It just works. Going kind of one ladder up, we need to start thinking about clusters, and as in many clusters. So to be able to cover this kind of archipelago of different sites and cloud providers, you will end up having multiple, and I mean really many clusters to manage. So we all know that cluster lifecycle management can be a bit slow and hard and daunting, especially from the control plane nodes point of view. I guess we've all been able to break down etcd. I've done it many times. Just last week, I found another way to break it down. So the second kind of piece of puzzle is a project called Cosmotron, which is kind of like a sub-project of K0s in a way. It really builds on top of Cluster API. What it actually means for us is that our clusters now become custom resources. So essentially, you can actually define the cluster configuration, the infrastructure configuration, everything as a set of custom resources. The super nice thing about that is that everything is now declarative, which means that you can start to do GitOps patterns for clusters. And also, we get standardized lifecycle model and operational model for every single cluster that we have. Now that we have capacity available for us through multiple clusters, our kind of GPUs and compute resource in general, it's still kind of siloed because it's dependent on a cluster in your typical model, which means that scheduling things, for example, is actually bound to a cluster. Kubernetes scheduler understands only about single cluster, of course. The third piece of puzzle is open source project called Cordant, where we build on top of Cluster API and Cosmotron and others, where we really enable fleet-level operation. What I mean by that is that you can actually start to schedule and deploy your applications across fleet of clusters. You can say that I want to deploy my fancy AI workload to every single cluster that has GPU resources, or matches this label, or whatever patterns you want to do. So we can actually start to treat the whole capacity and GPUs more like a shared pool of resources. I mean, of course, kind of almost physically thinking, GPU is bound to a cluster. But now we can actually access that at the fleet level. And more importantly, we get a homogeneous model how we operate our every single cluster and basically our whole fleet of clusters. And of course, observability is the same and everything.
All right, so now that we heard a little bit about those components, let's see how we use them to build up a platform or build upon them for a platform for geo-distributed training. And let's connect those back to the initial requirements. Just to recall really quickly, platform had to be provider agnostic, support heterogeneous hardware, and be Kubernetes native. So to comply with the provider agnostic part, we built up on Cosmotron, which allows us to run hosted control planes in a single management cluster. So basically, we can spin up a single management cluster, deploy Cordant on there, and then use Cluster API from there to onboard GPU nodes or attach remote worker nodes, so to say, from anywhere. So they do not have to be located in the same data center anymore. In addition, it allows us to separate the control plane traffic from the data plane traffic, which is quite essential for AI training later on. To support heterogeneous hardware, we're using K0s because, as Jussi said, it's a lightweight Kubernetes runtime which basically runs anywhere. Therefore, it also works great on heterogeneous hardware. And finally, we're using Cordant, which allows us to orchestrate this whole life cycle declaratively. Basically, Cordant has this concept of cluster templates, which are essentially blueprints for cluster API clusters that we can use to provide the blueprint for our ML engineers to deploy their own clusters and run their own workload on there with service templates that are used to deploy, for instance, the GPU stack, the GPU drivers, as well as the workload itself. So these components, therefore, allow for workflow that goes from creating a hosted control plane in a management cluster over to onboarding GPU workers and deploying the platform services, as well as the platform itself declaratively using templates. And since those are basically templates, right, or CRDs, we can put them in Git repositories and use GitHub's workflows to organize all of that, review it, and make it auditable. So basically, this is the foundation on which we build up this platform. And after we done the work and figured it out, we switched gears a little bit and moved over to a validation phase, in which we run different field studies to validate if it's possible to use such a platform to run geo-distributed AI training. Once, for instance, across heterogeneous hardware, and in another field study, we started a more dynamic approach where we used excess energy to train LLM models. So here you can basically see the setup that we created for our first field study, which was about the geo-distributed training on heterogeneous hardware. And let's address the elephant in the room first. Distributed training typically assumes that GPUs are co-located in a node or at least in the same data center and connected via fast interconnects such as NVLink or InfiniBand. This is obviously not the world we are targeting here, and therefore we intentionally violated that assumption for this field study and so created a setup where we started out with a management cluster that is located in Germany, where the whole Cordant and cluster API stack runs. And from there on, we attached GPU worker nodes from 2 different data centers. For instance, we used NVIDIA nodes that were located in Canada, and also AMD GPUs that were located in the US. So here, this whole field study was designed to validate whether we can make this cross-border and cross-vendor GPU resources work together as one operational training environment. And for such an environment, one of the most important things from a platform perspective, except obviously having the money to pay for those GPUs and then being able to find a GPU provider, which still has those GPUs available, is the cross-site worker connectivity. And for that reason, we basically created a Cordant cluster template in which we integrated the CNCF project Cilium as a Kubernetes CNI. And there we also configured Cilium to build up secure peer-to-peer WireGuard tunnels between the participating workers of the clusters. This, on the one hand, is great because it avoids a central VPN gateway through which all traffic would flow. And also, Cilium allows us to build up on their service mesh implementation to even connect clusters between each other. We also tested other overlay networks, but here for this case, we decided to use the Cilium and WireGuard approach since it keeps the networking closer to the actual Kubernetes data plane. And if you look one layer up, you can see some of the services that we installed on those clusters. And basically, since we want to run AI training, we need to get the GPUs to work, right? And in order to get them to work, we need to install drivers. And for that reason, we employed the NVIDIA GPU operator to install the CUDA runtime on the actual nodes that had NVIDIA GPUs, as well as the AMD ROC GPU operator that does the same for AMD GPUs. And then we also deployed Volcano. Volcano is another sandbox CNCF framework which enables gang scheduling, which is quite important for AI workload. Yeah, and then we started implementing the actual training, which was done by our engineers with PyTorch Elastic and then run as a Volcano batch job. And don't worry, this is not going to turn into a hardcore ML talk right now, but you can't really use normal distributed data parallel training in such a scenario because the latencies are way too high. And therefore, we built up our training method on an approach that is called DLOCO. It stands for Distributed Low Communication Training, and was published by Google. And we extended it a little bit and deployed or basically implemented our training algorithms on there. As I said, I'm not going to go into much detail here, but you can approach me after the talk if you're more interested in that part. So basically, we had our platform ready, and we also validated it by implementing different workloads. So basically, we trained different models from different workload classes in this platform, or on this platform, better said. For instance, LLMs, computer vision, graph learning, reinforcement learning, and audio. And that worked out actually quite good. We were able to achieve a comparable performance when it comes to the actual accuracy of the models later on, with some caveats that I'm not going to go into detail right now due to timing issues. But yeah, in general, this low communication training reduced the WAN pressure, the pressure on the internet level. If you're interested in the actual methodology about it, we published 2 papers about it and also open sourced the whole training implementation, or you can approach me if you want after the talk. Okay, so this was the first field study in which we basically assumed a rather static pool or environment of GPU resources, right? For the next study, we wanted to relax that assumption and target a more dynamic approach in which GPU resources can come and go over time. And the motivation for that actually stems from the sustainable computing domain. Because here, the point is that the renewable energy is often not always produced where and when it is needed. For instance, wind and solar power might be available in one region, like here on this slide in northern Germany, whereas the main consumers are somewhere else, for instance, in the south of Germany. And if the local demand is then too low, the grid is congested, or there's not enough storage available, this excess energy would go to waste. And this is something that is called a curtailment window. So basically, you have a curtailment window when there is potentially useful energy, renewable energy available that cannot be consumed, moved, or stored economically. And so basically here we asked ourselves, what if we could create some kind of elastic AI workload that could move towards these temporary windows of excess energy and use them to, for instance, train an LLM model. So that is what we tried out here in this field study. But this is not, again, not only a machine learning problem, but also obviously an infrastructure problem. Therefore, we require an elastic infrastructure orchestration layer. To walk you through our approach real quick, we basically assume that we have multiple geographically distributed sites available. Here, in this case, the site A currently has excess energy, so it is active and also training locally. Site B instead does currently not have a curtailment window, so it is not provisioned, the nodes are not running, it's not using any energy, and it's also not training. But then site C enters the curtailment window. And at that point in time, this site is provisioned, the nodes are prepared and attached to the training environment and can also start training locally. And as soon as we have multiple sites active, this purely local execution is switched to a federated mode, basically following the federated learning paradigm, where the model state is periodically synchronized between the participating sites and then averaged by, for instance, a federated averaging algorithm. And from a machine learning perspective, we implemented that using the Flower AI framework. This is like one of the biggest open source frameworks for federated learning right now. So all of that was mainly about the AI side, ML side, right? What did we have to change in the underlying platform to enable this training? And the answer is actually not much. It's exactly the same platform. We just integrated or added 2 further components. On the one hand, a curtailment signals API, which provides us those energy availabilities or curtailment window signals, if you want so, and a scheduling API, which receives those curtailment signals and then decides based on those data what site should be activated and what other site should be turned down. So basically it converts these energy signals into resource lifecycle decisions by, again, talking to Cordant, which then uses Cluster API to spin up a site, spin up a cluster, attach it to the training environment by installing the GPU operators again, starting the actual training workload, and so on. And here we even extended, or here we had to extend it by implementing a custom Kubernetes operator for this Flower framework, but this is still, again, cloud-native stuff, right? We all have probably written an operator at some point in time. And yeah, so this also worked out quite well, actually. And we were able to train a 500 million parameter transformer model on this infrastructure. And during the training, we switched between local and federated execution while preserving the training quality. And at the same time, we could reduce the operational carbon emissions by more than 90% in times compared to a baseline execution where only one of those sites would train the model. Again, we wrote a technical report about it. We also open sourced the code for that, which you can find here on the slide.
I wanted to point out that although this is about, or this field study was about these containment windows and model training, the exact same pattern can be used for any signal that you want to do. Yeah. Whether it's when your application users wake up and start to use your application like time-based things, or it doesn't matter what the signal is. You can use the exact same pattern, just match to the signal that matters for you and your applications and environments.
Exactly, yeah. All right, so what did we learn during these field studies? First of all, we learned that it is possible to run geo-distributed and heterogeneous AI workloads. So they are viable today, and building on top of this Cosmos ecosystem and Cluster API and the whole cloud-native ecosystem, we had a stable foundation where we could even go from a rather static training to a more dynamic approach without changing the actual underlying platform at all, which is great in my opinion. Another thing that we learned is that GPU lifecycle management can still be hard, especially for heterogeneous environment. I mean, it's not as bad anymore as the meme here on the slide may make you think, because we have these operators for NVIDIA and for AMD, but we still ran into a problem when we, for instance, used an instance which already had drivers installed, because then the actual NVIDIA operator in that case runs into problems, since there's already a driver installed, maybe in the wrong version, and then it fails, and then we couldn't run the AI training anymore. In addition to that, we had similar problems sometimes with the AMD operator, because there, when you want to automate the actual install form or the actual deployment of those drivers, you need to prepare images for each Linux kernel version the driver should be installed on. This is not a problem. We did that for like the last 10 versions of the Linux kernel. But then we tried to run, for instance, on cloud providers which have their own kernels, and then it didn't work out again. So yep. It can still be a hassle. It's not as bad as it was, but yeah.
It's still not great.
It's still not great, so to say. Great, yep. Yeah. Yeah. Finally, secure peer-to-peer networking works, but the latency-sensitive training still needs care. And this also brings me to the last point I want to make here, that the platform and workload must be co-designed. You can create a platform like that. You can connect it. It can look like an operational platform, even though these remote workers are globally distributed, but as long as the training does not take the latency, for instance, into account, it's not going to work out. So you have to work on in both directions and combine the work there.
Absolutely. And one thing I'd want to point out also is that one of the kind of enabling concepts was the whole fact that through Cluster API and all the other tooling that we introduced, everything is now declarative, which is actually the enabler to build all this scalability and implementing the containment windows and deploying clusters like very, very dynamically. Yeah. So that's definitely a direction to look into in your use cases too.
All right. With that, thank you very much for your attention, and we can open the Q&A session. Yeah, the first question I actually anticipated, because I also watched this talk yesterday, and Yeah, this is actually something we're currently looking into. We started out with the training side of things, but inference is definitely a case which would also work. And I think Mohammed yesterday even described a scenario or an architecture which is quite similar, right?
Yes.
And could work for that.
It absolutely will work for that. Of course, it depends on your application, whether your application stack allows you to, or the nature of your application allows you to do this. But from the like Hami, Kaito, Cluster API point of view, it'll work exactly the same. Because in the end, those are things that you deploy as pods in your cluster, so it doesn't really change the equation that much.
Mm-hmm. For the second question, which is about the networking side of things, we are basically using Cilium here, right? And for the actual AI training, we don't really need ingress because the AI training is deployed via GitOps. Our developers could just hit an API and then basically deploy the actual training. So there we don't really need ingress, right?
Yep.
It is more important for inference scenarios, actually.
Absolutely, yes.
Yeah.
And for those use cases, I don't know if Yuri is still around, but there are very nice tools in the CNCF ecosystem. For example, this KGB, the global load balancer thingy. I don't really know much about that, but I know that it exists, and so you can absolutely make it work for inferencing and basically any other types of workloads too. How does the DNS side works? Well, when does DNS actually work? Well, that's kind of outside of the platform per se. But I bet you can do like geo-distributed routing through DNS too, if you really are up to that. Kera for scaling with the cluster API. To be honest, I haven't tried and looked into that much into Kera for cluster API. I do know that you can actually integrate the so-called standard Kubernetes cluster autoscaler with cluster API so that the autoscaler would actually scale up the machine deployments in cluster API. With that pattern, which I really, really like, because in that case, you don't actually have to configure the autoscaler to talk to Amazon or Google or whatever at all. Autoscaler only talks to cluster API, which is kind of the abstraction in between. So it makes the configuration and setup very, very simple.
Mm-hmm. Yeah, if I may answer that one. We actually validated, or we conducted the speed studies in order to validate how stable it really is. And I would say from a platform perspective, it's quite stable, actually. All those cluster API things and the magic behind it works quite well. What sometimes makes issues or has issues here is the actual ML side, the workload side, which also refers back to the last point I made in the lessons learned. Both of them have to be co-designed and co-developed. And this is actually an ongoing process. Google just released a new paper where they extended the DeLoco approach, for instance. And then we have all those different federated learning approaches, which also work for that reason and make it hopefully more stable. Yeah.
Yep. All right. Thank you. I think the timing even